every finite, which we call the lower polynomial, and which turns out
there seems to be some feedback. If I guess I don't know if people should be muting or something. Or... Now I cannot hear the audio.
There might be some technical issues.
Yeah,
let us wait.
The audio.
Yes, sir. Yes. Give us a minute. We will sort it.
online. So hello everyone, and first of all, thank you to the organizers for inviting me to speak at the ICLAA. This is my first time attending and participating in the ICLAA, and of course it's in hybrid mode. I myself am presenting online, so hopefully the next time this happens and I'm able to participate, it will be offline and we will all hopefully meet in person. And so yeah, so today I'm talking about this new kind of construction from arising from every single finite, simple, and connected graph, which we call the blow-up polynomial, and which turns out to have nice connections and nice properties to several different things. So all of this is joined with my postdoc, Rajesh Chaudhary. To set some notation, so let us start with the graph. And for us in this talk, all the graphs are finite, simple, unweighted. There are no extra edge weights or whatever kind, and most importantly, connected. Okay? And so every graph will be denoted by two finite sets, V of vertices. In the second part of the talk, I will usually refer to them, number them maybe by 1 through k for some positive integer, and E contained in V choose 2, meaning pairs of distinct vertices, and that's called the edges. If a vertex pair occurs in E, then those vertices are said to be adjacent, and so on and so forth. Right? Now, because the graph is connected, between any two nodes, there is a path. So you can find some finite sequence of edges such that you go from one to the other. And therefore, you look at all the possible paths connecting two nodes, look at any path of the shortest possible length. Okay? That length is what I care about. I call that as d of v comma w. This is clearly always non-negative integer because those many edges join some shortest path between v and w. And now the only thing is that this is always non-negative, but in fact it is 0 if and only v equals w. Otherwise, it is strictly positive. Okay. So now you arrange all these numbers in a matrix, the distance matrix of G. This is a V cross V or size of V cross size of V matrix with the entries dVW. So all the diagonals are 0. Okay. Now one interesting quantity that has been studied quite a lot for the distance matrices, specifically for G, a tree, is the determinant of this distance matrix. So trees are precisely graphs with no cycles. So this is an example. These are all trees. This is called the binary tree, I guess, or the two regular tree. Every parent has two children. This one is the star graph because there's one vertex joined to lots of others, to all the others. Right? So that's a star graph. This is an example of a complete bipartite graph. These are all trees. Okay. So our paper, or this work, is motivated by two sort of classical, if you will, facts. The first fact is algebraic. It's 50 years old. So the idea is to look at the determinants of distance matrices of trees on the same number of vertices. So here are the only two trees up to isomorphism or relabeling on 4 vertices. One is the star graph, K13, and one is the path graph. Both of them have distance matrices which are 4 by 4. All the diagonal entries are 0. And then, of course, like 1 and 3, the distance between 1 and 3 is 1 edge, so 1 here. Distance between 1 and 3 is 2 edges, so 2 in the 1, 3 entry, and so on. Okay. It turns out that both of these matrices, 4 by 4, have the same determinant. It's a beautiful fact. The reason is also equally or even more beautiful. But anyway, we won't go into the reason. But both matrices have the same determinant, and remarkably, this is actually true in much more generality for all the trees. And this is this famous 50-year-old result by Graham and Pollack. Given a tree on k nodes, the determinant of the distance matrix is purely a function of k. There is no dependence on the tree structure. Okay, so this is the provided to us our first motivation. We wanted to look at other graphs, other families of graphs for which the determinant of the distance matrix is a nice function. Yes, I will mention this on the next slide. I'll write it out. The second fact which motivated this work is from analysis, from the spectrum or spectral theory. Namely this, so again, Ron Graham again studied the analysis side or the spectral side of distance matrices, for example, with Laszlo Lovász in the 1970s. Okay? And so the question that one naturally, and then this has been studied many more times in the future in many papers, and one question that's natural to ask is the following. It is clear that the distance matrix itself detects the entire graph. That gives you the entire graph, because just look at the entries which are 1. Those correspond to the edges, and they're off diagonal because the diagonals are 0. And once you get the edges, you have the graph. Okay? The question is, do the eigenvalues of the distance matrix also determine the graph? Meaning, or in other words, does the monic characteristic polynomial detect the graph itself? Okay? The answer turns out to be no. There exist graphs, two graphs, for example, these two graphs here, with the same number of nodes. So the matrices have the same size, the characteristic polynomials have the same degree, and the characteristic polynomials both agree for these two graphs, but these two graphs are clearly not isomorphic. For example, here is a vertex of degree 4, and there is no vertex of degree 4 in the first graph. Okay. So in particular, we conclude that the characteristic polynomial here of the distance matrix does not detect the graph up to relabeling of the nodes. Okay. This leads to our two interrelated goals or motivations. First one is to find a family, GI, let's say indexed by some set I of graphs, for example, the family of trees on a fixed number of nodes, such that the function taking I to the determinant of the distance matrix of GI is nice. For example, for this family of trees, the function was the constant function, which was purely a number in terms of k that we saw. Okay? Because that we want to find other such families, but more importantly, this should relate to the second. That's why they're interrelated. This motivation or goal should relate to the second one. This family should help us find an invariant of this distance matrix which truly detects the graph. Okay, so of course the distance matrix itself does, but I mean, that's not very subtle. That's not very deep. We want some kind of a polynomial invariant, maybe, or some nice thing, or of the determinant matrix. That kind of thing, which detects the graph. And obviously, also at the same time, you want that invariant to be related to the distance spectrum or to the characteristic polynomial, to the eigenvalues of the original matrix DG. Interestingly, the goal of this talk is to tell you that indeed these goals, these motivations, these aims are realized with the same one and the same object, and that's the object I want to tell you about. It's called the blow-up polynomial of the graph. And the family here is called the blow-ups of the graph, or the graph blow-ups. Let us first begin with that family and then come to the invariant. Okay? The key construction then, which will answer both of these questions and reveal many more interesting facts besides, is that of the blow-up of a graph. So the idea is, take a tuple of integers, positive integers, NV, I'm indexing them by the vertices, okay, and I'll call the graph blow up as G bracket N. This basically is again a finite, simple, unweighted, connected graph. The vertices are as follows. For every NV integer that I chose, take that many copies of the vertex V. And now connect all the copies of one vertex with all the copies of another vertex, if and only if those two original vertices were connected in the original graph. Then you connect all of them. You get a complete bipartite graph on those copies and copies. And if the original two vertices were not connected, then the copies are also not connected, no edges. Yes, that's what the second line says. Let me give you some examples. The first example is that of a path graph. So forget the vertex C for now. Okay, look at just AB. Okay, and now I blow up I keep only one copy of B, but I take two copies of A. Now because A was connected to B, the other copy, which I call C, maybe C for copy, I guess, is also connected to B, but A and C are not connected. Okay, so that's the other thing I should have said here. Because I'm lacking self-loops in my original finite simple graph, V is never connected. A copy of vertex V is not connected to another copy of vertex V, because V was originally not connected to V. Okay, so therefore here A is not connected to C, and the path graph on 3 letters, on 3 nodes, is the blow-up of a path graph on 2 nodes. Here are some 2 other examples. One is the star graph I showed you. Well, that is exactly the same as saying start with one edge. and blow up the other vertex to n different copies and keep only one copy of the other edge. And that's exactly the star graph. And similarly, the cycle graph, start with one edge, let's say 1, 2. 1 is joined to 2. Now create two copies of 1, namely 1 and 3. Create two copies of 2, namely 2 and 4. Because 1 is joined to 2, therefore 3 must be joined to 2. So now 1 and 3 are joined to 2, and creating a copy of 2, which is 4. So 1 and 3 are also joined to 4. And of course, 1 and 3 are copies, hence not joined. 2 and 4 are copies, hence not joined. Okay, so these are what they are. These are examples of blow-up graphs. They're both blow-up graphs of the edge on two nodes. Okay, so now as I said, the idea was to look at determinants, right? So let's look at the determinant of all these blow-up families. So in all of these examples, one can explicitly calculate these determinants. I won't tell you how, because in fact one can do this in much more generality. But anyway, so one can calculate these, and it turns out to give you the following expression. It's a very, very simple expression, very clean expression. And it consists of two parts. One is an exponential factor and exponential of r plus s. R is the number of copies of the first vertex, s of the second vertex. And then the polynomial in the R and S. And notice that interestingly, the interesting thing is the distance matrix here is only going to consist of zeros or ones or at the most 2. The sizes of the distance matrix include R and S. And this is a function of the sizes. So that's the interesting thing, right? And even the exponential features the r plus s, and then the polynomial is in terms of r and s separately, not r plus s. So that's something interesting. Fine. The question is now, what is the determinant for both general graphs? This is a very special case of two letters or K2. But what about the determinant of Gn for general graphs? Does it have something similar as a formula? And the answer turns out to be yes. This is our first result. There exists a real polynomial Pg of n, where n denotes the sizes. So the arguments of this polynomial are the sizes of the matrix. It's not that the sum of the family of graphs gives you some kind of nice formula in terms of the entries. It's actually a formula in terms of the sizes, which is sort of very strange, maybe, or very really less frequent. For all, and this formula is true, the following happens. The determinant of the distance matrix of the blow-up is first of all minus 2 raised to something exactly similar to r plus s minus 2. It is this formula, summation of size minus 1, times some remaining factor, and that remaining factor is a polynomial, a real polynomial. In fact, with integer coefficients, but okay. And this equation is true for every single tuple of positive integers. There is one polynomial to rule them all, if you will. Moreover, this polynomial is multi-affine. So you see, there are no r square terms here, no s square terms or higher degree terms. These are called, so if there is a polynomial with linear degree, that's called an affine polynomial, ax plus b. And even in two variables, such polynomials are called multi-affine because there are no quadratic or higher terms in any of the variables. And that is what exactly happens in general for every graph. PG is multi-affine. It has constant term -2 to the, so forget now this exponential factor, just look at this one. The constant term is -2 to the number of vertices. The linear term is minus of that coefficient times r plus s, or in here, summation nb. And in fact, we have a closed form expression for every single monomial, and that's a different, yeah. So it's not too hard to work out. And for the full details, you can look at our paper online, on the preprint of the archive. Okay, so this polynomial, this real polynomial is what we define to be the blow-up polynomial of G. And it governs all the sizes of the blow-up. So this is a very nice equation. This attains the first goal, wherein, the determinant of the, so here the family is parameterized by the bold n tuple, G of n. That family for every single graph G, n mapping to this determinant is, you see, this nice exponential function times this nice polynomial function. So that recovers the first goal. You understand some nice behavior. And now the second goal is about connecting this to the distance spectrum and the characteristic polynomial and so on detecting the graph. Before I go there, let me mention one thing about the proof of this formula, of this theorem. The proof uses something called Zariski density from sort of commutative algebra, but basically very algebraic proof. So the idea is we first of all define the modified distance matrix to be exactly this much. And this other symbol, the delta n, as the diagonal matrix with the sizes of that. Then the proof above reveals the following. Take -2 raised to negative of that power times the determinant. Okay. The proof, you can check the formula, but the calculations reveal that this thing, which we want to prove is equal to this guy, or well, we want to prove is a polynomial, turns out to exactly equal this determinant. And the determinant, of course, is a polynomial, and that is why PG of n is a polynomial. This is really what is PG of n. Right? So this proof is what the proof reveals this equation holds. You see both sides, there is no notion of mg being invertible, for example. Right? I don't need mg to be invertible. It's not needed in either side of the equation to claim it. But to prove this equation, the actual inverse does get used. So how does one assume in general that no, this is invertible over R? Because of course it need not be. For example, if the let's see. Yeah, well, you can find examples where the distance matrix is not invertible. I will in fact come to that later on. Okay, so yeah, well, let's see. Okay, fine. So first of all, the answer: how do you assume in general that you can assume some matrix to be invertible? You assume it using Zariski density. The idea is you proceed in a few steps. You work first of all over the field of rational functions. So first of all, you assume that mg consists of variables, indeterminates. I know that it equals some integers, but we will specialize these indeterminates to integer values. So we are actually going to show that somehow this formula holds in far, far greater generality. Right? First of all, work with mg as the variables, the mvw's, and look at the field of rational functions with rational coefficients in those variables. Then the determinant is a non-zero polynomial in these distinct variables. Therefore, it's non-zero, and therefore it's a unit in this field. And in this field, whenever it's a unit, then our proof works. Because as I said, we have a proof where we just need to use the fact that this matrix is invertible. So when this field is working, then it works. But now we observe that both sides of this equation turn out to be polynomials. So some of you have to, because there is no mg here. These are polynomials in the variables. So the equality in this field therefore holds not just in the field, it holds in the polynomial subring, not only in rational functions. These are polynomials, so the equality is an equality of polynomials. But now, you see, polynomials are the same over an infinite field as polynomial functions. So the equality holds in this ring of polynomial functions, Q adjoin this thing. And then you notice now that the coefficients of those polynomials are integers. So it holds in the polynomial function subring with integer valued coefficients. And now, once it holds in this ring, you can just perform evaluations and specialize to any commutative ring via the evaluation of homomorphisms. And sorry, not yet. Then the point is it holds on this ring, but not at all possible values of MVW. It holds whenever the MVWs are invertible. That's the whole point. The matrix is invertible. So it holds on the non-zero locus of this non-zero polynomial. And now, because this non-zero locus is Zariski dense, because the polynomial is non-zero, therefore any equality of polynomials that holds on the dense set, Zariski dense set, holds on automatically by continuity, if you will, by density on every value. So the equality holds over all values, and hence in this subring of polynomial functions, and therefore now we can specialize to values in any commutative ring, and we get that. That's how one proceeds slowly. And so that's how one proves the theorem. Okay. Okay, so I'll just, and this Zariski density is a very powerful technique, is the point. You can sort of assume that such a matrix is invertible, whereas you could not earlier. It really relies on the fact that the determinant is a polynomial, and polynomials can extend by density to closures, Zariski closures. Okay, so now what we just said is that therefore PG of n is actually this formula. We proved this in the course of the previous slide in the paper. This is a polynomial in the entries of Mg as well as in the sizes, as you can just see. And therefore, in the above proof, we also in fact turn out to work with the sizes being indeterminates, and one has to do a little more careful calculations and reasoning there, but it works out. Once that happens, we work over, Therefore, in the rest of the talk and in the paper, we use the NV to denote both the sizes, the integer sizes, as well as the variables. Okay. So now, what we just said, therefore, is PG of n is a multi-affine polynomial in these sizes. For example, this is the polynomial here for the edge on two nodes. The coefficient of every monomial, as I told you, we can calculate it. It equals some power of -2 times the determinant of the principal submatrix of Mg. Mg, remember, is the distance matrix, the usual matrix, plus twice the identity. Okay? And you look at some principal submatrix, the determinant times some power of -2, that is the coefficient. And so you can explicitly compute stuff. So this, first of all, achieves the goal that the function taking the indexing variable n, the tuple n, to the determinant of the distance matrix is a nice function. What about the second goal? Can this polynomial recover the graph? Okay, so that's the next question. Before I answer this question, let me look at a related polynomial to the blow-up polynomial. It's the univariate polynomial where I set all the nv's to be equal to n. So remember, n here is a variable, not just an integer. We can even substitute real numbers or complex numbers, which we actually will. Okay, so the univariate blow-up polynomial is UG of n is PG of n, and this is closely related to the characteristic polynomial of the distance matrix. Why? So that's the next result. A real number is a root of UG. And now see, I'm saying n, but I'm saying it's a real number because it's a variable specialized to the real line. Is a root if and only if, first of all, n cannot be 0. 0 is never a root. And then because n is not 0, you can define this thing. And this is a root, in fact, an eigenvalue of distance matrix. And with the same multiplicity. So somehow, yeah, that's the same as saying that 2n inverse is an eigenvalue of mg, UG, dg plus twice identity. Or you can divide mg over 2 and say n inverse is the eigenvalue of mg over 2. So it's really, this univariate polynomial is really the inversion of the characteristic polynomial of mg over 2. But anyway, that's why it's very crucially related, closely related to the eigenvalues of the distance matrix as well. In particular, the same two graphs that I told you again demonstrate that this univariate polynomial certainly does not recover the graph itself. It's equal for both of these graphs, but the graphs are non-isomorphic. So that again leads us back to the same original question, the same second goal that we had. Does the multivariate blow polynomial, the original one, recover the graph? Okay. So let me first talk about a weaker question. If G has an automorphism, so for example, automorphism, I mean, if you look at a relabeling where 7 and 8 get switched, the entire graph stays isomorphic, nothing changes. So that's an automorphism. Or 3 and 4 get switched here, or 4 and 5 get switched here, and so on. Right? So if G has such an automorphism, sending a vertex V to W and vice versa, then the blow polynomial is symmetric under these two vertices being exchanged. Right? Therefore, the self isometries or automorphisms determine the symmetries of PG. The question is, does the process work in reverse? If I know how my blow-up polynomial is symmetric in the variables, can I understand the automorphisms? So that's a weaker question. And of course, the stronger question was, does the blow-up polynomial tell me G itself from which I could gather the automorphisms of G? The answer turns out to be yes for both of them. That's our next theorem. The symmetries of the polynomial itself, blow-up polynomial, are exactly the same as the self-isometries or automorphisms of the graph itself. And more strongly, the purely quadratic or Hessian part of the polynomial actually already recovers G. I don't need the higher order terms. I don't need the linear terms. I don't need the constant terms. The Hessian alone is enough to recover G. And it's because there's for all graphs, you can actually perform the explicit calculation and you check that you get some power of -2 times the all ones matrix. Subtract some power of -2 times certain formula from which it is very easy to derive the original distance matrix. So the Hessian matrix gives you the distance matrix clearly gives you the Hessian matrix. And so this answers our other goal as well. And so now we do have this nice family called the graph blow-ups, whose determinants behave very nicely with respect to the tuple as a function of the tuple. And the determinants themselves are multivariate polynomials in the sizes, in the tuples, which turn out to recover the entire graph, which are related also to the spectrum, the distance spectrum. So this multivariate blow-up polynomial and family of blow-ups achieves all of these goals. Okay, so that's nice. I think now that ends the first part of the talk about the blow-ups and blow-up polynomials. Let me now focus on, in the last 7 or 8 minutes, let me focus on some other properties of the polynomial. So first of all, remember the polynomial UK2, of PK2, right? Where was this? Here. This one. This is the multivariate polynomial. Now let me specialize to the univariate polynomial. So I take n. So 3n square minus 4n minus 4n plus 4. Right? This is this much. And this clearly factorizes. So it is real rooted. This is for K2, but I can also blow up the complete graph on K vertices for any K. And you can check that if you take UK K of n, then you get again a real rooted polynomial. So it's very natural to ask, well, is it real rooted for every graph? The univariate polynomial. The answer turns out to be yes, but in fact, much more is true, and not just for UG, but for PG as well. And that is that the polynomial PG for every single graph is real stable as a function of the n's. Okay. So I remind you that a polynomial is said to be real stable if, and now from now on, I will switch the n to z, z1, z2, zk. So first of all,
The slide is not loaded up, so I don't know. Should we pause and start again?
like this VS size k, this graph, and
I don't know what happened, but now the correct slide is there. Thank you.
Sir, is it not moving?
Yeah, now the correct slide is there, but consistently last few slides, somehow my audio is going ahead of my video. I don't know why. Anyway, now this slide is correct now. Yeah, yeah, yeah. You can continue the talk. Thanks.
here there are k variables and so on. And also z1, z2, zk, because from now on, I will think of this polynomial as a function of complex variables. So let me just use z's for the variables. So a polynomial in k complex variables is real stable if and only if or whenever this polynomial is non-zero, provided all the variables lie in the upper half plane. It's like saying all in multivariate real polynomials, if everything is in the positive orthant, then the polynomial is non-zero or something like that. So the same kind of thing. All the variables lie in the positive complex orthant, basically the upper half plane. Then the polynomial does not vanish. Okay, that's the definition. But the point is, real stability has been extremely well researched in recent times. It has been a very hot topic and has led to some spectacular advances in mathematics, primarily maybe due to the works of Borchea and Brandon, who provided all these far-reaching generalizations of the Lagrange-Schur program. They developed some multivariate Zas principle and Jensen multipliers, incorporated the Lee-Yang program and the Heilman-Lee theorems into a big framework, proved 3 long-standing conjectures of Charlie Johnson, and so on and so forth. And these progresses were then taken forth by Marcus Spielmann and Srivastava in proving the Caddison-Singer conjecture and existence of bipartite Ramanujan graphs and so on. So some spectacular sort of highlights in modern mathematics come from real stability and its study. And so these polynomials that I mentioned provide new examples of such real stable maps. Right? And they arise, interestingly, from graphs and distance matrices. Okay? I'll mention a couple of ingredients in the proof of this theorem. One is a result of Brandon from 2007, which says that if you have positive semi-definite real symmetric matrices and just another real symmetric matrix, then this function of k complex variables, so take the linear combination with those variables as coefficients and add the matrix B to it, take the determinant, this is real stable. And the other is that inversion preserves real stability, which means that, like you can fix any variable and then invert the coefficients sort of and put minus signs alternating. And that if the original polynomial was real stable, then so is the new polynomial. Okay. So these two facts turn out to sort of, and obviously some clever determinant calculations turn out to prove this theorem. Excuse me. So now let me go beyond real stability. So I remind you from the very first result I mentioned that the multivariate blow-up polynomial has this as the constant term, minus 2 raised to v, if you will, and linear term is this thing. So this already shows you immediately that this polynomial cannot satisfy 2 further sort of desirable properties. Clearly, the coefficients of the constant and linear terms are of unequal signs. So that's the first property. To bypass that, one can try to consider PG of minus z. So then when you consider minus z, the minus goes inside and the signs stay the same. But then, of course, one must check if the higher order, the quadratic term, the cubic term, are those signs also the same? Maybe they are, maybe they are not. When are they the same? Similarly, there is a constant term and there's a linear term. So clearly the polynomial is not homogeneous. And for that one, there's a standard trick, in sort of projectivizing the polynomial or homogenizing it, and that's this thing. So if I want to bypass both of these operations, then I have to take a minus inside here. I have to put a minus sign and then put this. Okay. And so anyway, but why would I want to bypass one or both of these obstructions or objections? So stable polynomials with these additional properties were studied even more broadly than just saying stable polynomials by Borchea, Brandon, and Liggett. They were called strongly Rayleigh polynomials or strongly Rayleigh distributions, the coefficients of the same sign. And homogeneous stable polynomials were more broadly studied as Lorentzian polynomials very recently by Brandon and Ho. So the question therefore is, if we homogenize P at -1, meaning do both of these together, for which graphs does this actually yield a polynomial in this class or in this class? And our next result exactly characterizes these polynomials. And remarkably, the answer is if and only if all the coefficients have the same sign. So the answers to both the questions are actually the same class of polynomials. And they are a very familiar class of polynomials, a very familiar class of graphs. Which ones? The ones in the title, the complete multipartite graphs. So let's, without further ado, this is maybe, I think, my second last or last result. So given the graph as above, define its homogenized blow-up polynomial exactly the way I told you. Put a z naught. I can ignore the sign outside because it's just a scalar, but put the minus z naught here, okay, and homogenize. Then the following are equivalent. This polynomial that I mentioned is real stable if and only if all the coefficients are of the same sign, in fact non-negative. If and only if this normalized, so basically take this polynomial without the z naught, but with the minus sign, and divide by PG of -1, -1, -1. That is literally the sum of all the coefficients. So you get a polynomial whose coefficients are all non-negative and add up to 1, which means that they form a probability distribution. The claim is these things happen if and only if that distribution is strongly relevant. And these are all if and only if the graph is complete multipartite, which, by the way, is precisely the same as saying it's a blow-up of a complete graph. Think about it. So why blow-up of a complete graph is the same as complete multipartite graphs. Okay, so this provides a novel characterization, therefore, of complete multipartite graphs in terms of real stability or the strongly Rayleigh nature of this homogeneous polynomial. But in fact, it also provides the same characterization in terms of the Lorentzian nature. And so here are 4 other equivalent characterizations. The graph is complete multipartite if and only if any of the next 4 conditions holds. The modified distance matrix that I mentioned is positive semi-definite, or the polynomial that we just saw upstairs is Lorentzian or strongly log concave, defined by Gurwitz in a different context, or completely log concave. So these are all the same kind of, these are all equivalent to the graph being complete multipartite. And so these are all new characterizations, novel characterizations of that class of graphs. Okay, in my penultimate slide, then I'll just, maybe my last slide in some sense, I'll just say that the graph blow-up and the blow-up polynomial, which we so far talked about only for finite connected graphs, in fact, actually can be defined, and all of these results can be proved for all finite metric spaces. So not all, there's one result that doesn't go through, which is that G recovering from PG, the metric space itself cannot be recovered from its blow-up polynomial, because the distances can sort of differ. The minimum distance is no longer 1. It can be any real number. But there is a partial sort of progress in this direction, which is the following. The blow-up polynomial is certainly fully symmetric if and only if G has complete isomorphisms. It's completely symmetric, meaning that the graph has to be complete. If there is one edge anywhere, there can't be a gap anywhere else. So it's fully symmetric, the polynomial, if and only if the graph is complete. And this generalizes to the following result. For a finite metric space, with distance matrix dx, I can again define the blow-up polynomial, and this is fully symmetric in these variables if and only if x is discrete, meaning there is some positive number such that the distance between 2 points of x is either 0 if they are the same point, or that positive number c for every other unequal pair of points. So in that sense, this generalizes the situation in the complete graph case to all metrics, to discrete metric spaces. Okay, and let me end here. For lack of time, I'm sort of omitting results on some combinatorial extractions from these results called delta matroids, which we also obtained in our paper. We obtained one new delta matroid for each graph and a second new delta matroid for each tree. But there's no time. I will refer you to this preprint for the full details. Thank you very much. And I guess that's the end of the recording of the talk.
So it's time for questions from the audience.
Participants, please raise your hands if you have any questions so that we can unmute. Sir, I think there are no questions.
So thanks the speaker for his nice presentation on polynomials.
Thank you, Professor Apurva, for spending your time. It must be very late night for you.
Thank you. Yeah. It's not too late, but yeah. Thanks again.
So now we invite the next speaker. Is Professor Sriramakrishnan around?
Sir, he did not join.
Not joined. Okay.
Yeah, I don't have his number to contact. Maybe we'll proceed with this recorded talk and hopefully he will join us.
Let me text him. I'll call him.
He will be joining us in the afternoon again for Lal's session. We can reserve some questions for him.
I'm calling. He's not available on phone. Sorry, he's not available on phone.
Okay. Okay, Raksha, let us proceed with this.
Proceed with the recorded talk.
Yes, sir.
And Mukesh. I want to start this talk. I'm going to talk about inequalities among two-row determinants of Q Laplacians of trees and odd height peaks in generalized dig paths. So this is joint work with Arvind Lal and Mukesh. And this talk is dedicated to the memory of Lalda. Let me start with the definition of immanence. So if you look at the definition of the determinant of a matrix, an n by n matrix A, you see this expansion which is due to Laplace, the Laplacian expansion. This is very similar. You get sine of permutation. You sum over all permutations phi in Sn for an n by n matrix. The determinant is defined as sum over all permutations phi in Sn, sine of that permutation times the diagonal product corresponding to that permutation. Yeah. So we want to try to generalize this definition. So let lambda be a partition of the number n. So that means it's a number partition, and let A be an n by n matrix. Yeah, and chi lambda will denote the irreducible character of the symmetric group Sn indexed by lambda. So this is some standard basic from representation theory. Yeah, we think of this chi lambda as a function from the symmetric group Sn to Z. Yeah. And with respect to this function, you define d lambda of A. Yeah? So you see, it's very similar to the definition of the determinant, except that instead of the sign, you have this chi lambda of phi instead of sine of phi. So this definition is very, very similar to the definition of the determinant. Yeah? And this is called as an immanent, this function of the matrix A indexed by the number partition lambda of the number n. So n is the number of the number partition, lambda is a partition of the number n, and A is an n by n matrix. In which case you get this definition, and this is called an immanent indexed by lambda. So immanents of positive semi-definite matrices are well studied. And if you look at the representation theory of Sn, it gives us several such functions. Yeah, chi lambda in the form of irreducible characters. In fact, gives partition of n many of them. Yeah. So these are standard facts from the representation theory. You don't need them actually. You don't need to know that there are partition of n many and all that. So you just index by a partition lambda, you get this function chi lambda. That's all we want. So this d lambda of A is called an immanent of A indexed by lambda. Yeah. So you can ask for more general functions. Why only functions that appear as irreducible characters? What about arbitrary functions? That will also study. Generalized matrix functions are studied. So you take an arbitrary function f from Sn to Z and define exactly the same way. That will also give you df of a. Yeah, that's another way to get this. So when f is the sine function, that is sine of phi, then of course the immanent corresponding to the sine function is the usual determinant of it. Yeah? And if f is the identically one function, the all one function, yeah, defined as phi equal to 1 for all pi in Sn, then the determinant with respect to the identity function will be the permanent of it, because if you sum here, instead of sine of phi, if you change it to 1, you will get the definition of the permanent. So we get the permanent of it if you change the function to be the all one function. So this sine function from Sn to Z and the all one function, they are all both are irreducible characters of irreducible representations, and as mentioned before, the Sn has Pfn characters. So because they are partition of n, we define it as, the index set for partitions will be this lambda partition of n. This is a notation, standard notation for saying that lambda is a number partition of the number n. Yeah. So we need normalized immanence, so which is defined as, take the immanent of A divided by the immanent of the identity matrix, or you can divide it by the dimension of the irreducible. Both are the same. Yeah? This immanent of the identity matrix indexed by lambda is the same as the dimension of the determinant. So this we will study. So the starting point is this theorem of Schur, who showed that for Hermitian positive semi-definite matrices, n by n matrices, the normalized immanent is greater than or equal to the determinant. Yeah, this is all for all partitions lambda. Yeah, and if you recall, this determinant of A for a positive semi-definite matrix is non-zero, is non-negative. So thus all immanents of positive semi-definite matrices are non-negative. You get this. So Leibniz has conjectured that for the same class of matrices, permanent is the largest normalized immanent. So this means that the determinant is the smallest normalized immanent, and permanent is the largest normalized immanent. That is a conjecture. It's still open. So when n is fixed, it's permanent of A is greater than d bar of A. This is all right. So when n is fixed, let hook k, that is, so you have a partition with k parts. You can draw the Farrow's diagram, k parts and then all ones. Yeah. So it's considered a hook because of the hook length formula and all that. So this k, 1 power n minus k. Let this be a hook partition of n, and you denote the normalized immanent of A indexed by this hook k as hook immanent k of A. So Hayfron proved that there is a monotonic property, that is determinant of A is the first hook immanent, is less than or equal to second hook immanent, less than or equal to nth hook immanent, which is permanent. So this nth hook being the permanent and first hook being determinant, that follows on representation theory. That's you don't need. But this still doesn't prove Leibniz's conjecture. It just says among the special set of number partitions, the permanent is the largest. That's what it says. And there is a order here. Yeah? But this is true for arbitrary positive semi-definite matrices. So Merrill suggested that this Leibniz's conjecture seems to be tough to prove. So he suggested either you restrict the class of matrices, and in particular, maybe look at Laplacians of graphs. And he made some stronger conjectures about hook immanents of Laplacians of trees, and that conjecture was proved by Chan and Lang. So Merrill's conjecture is, it's a refinement of Hayfron's conjecture. Hayfron says that hook immanent k minus 1 of A is less than or equal to hook immanent k of A. If you take the Laplacian of a tree L, that's known to be positive semi-definite. In this case, special case, you get slightly refined inequality. That is not just A less than B, but A is less than, let's say, 0.9 times B. So this is a fraction, which is k minus 2 by k minus 1 is less than 1. So you get something better than what Hayfron's result gives you. All right. So Q analog of this result is also known. So this Q Laplacian of the tree is defined to be I plus D minus I into Q squared minus QA, where D is the diagonal matrix of degrees. So clearly, if you set Q equal to 1, Q squared will be 1, and this minus QA will become minus A. So it will be I plus D minus I minus QA, which is D minus A, which is the usual Laplacian. So this Q analog of the Laplacian it has entries which are polynomials in the variable q, and if you change the q, you can plug in values for q. Q equal to 1 will give you the usual Laplacian. Q equal to some other values will give you different matrices. So what we could prove, that is Mukesh and myself, is that if T is a tree on n vertices, and let LQT be the true Laplacian, then the hook immanents satisfy this. So something similar to what Hayfron proved. But in general, this Q Laplacian is not positive semi-definite for all Q. It's only positive semi-definite for Q between -1 and 1. That's the theorem of Buffett, Lal, and Pati. So this, even for arbitrary Q, we get this result like Hayfron's theorem. Yeah? And slightly stronger version is true for this. We get something here. The right hand side and the left hand side are same, but in the left hand side you have to add an additive factor, q squared minus 1 by k minus. And you have to add the additive factor. Okay. So the aim of this talk is to give a result similar to this result. So this gives you a result about some hook immanents of Q Laplacians of trees. They have some ordering. That is, you can, depending on the number of parts in the first number of length of the first part, there is some ordering for the immanent. So similarly, you want to do something here. So the setup is the same. T is a tree with n vertices, and LTQ is a Q Laplacian. Now we are looking at not hook partitions but 2-row partitions. Yeah, and 2-row is so a partition of the form n minus kk. Yeah, so it has at most 2 rows. So I want k to be non-negative, and since lambda is a partition, we must have k at most n by 2. This floor ceiling you have to be careful, because n minus kk is when we write it, we assume that n minus k is greater than equal to k. We always write partitions in weakly decreasing order. So n minus k has to be greater than or equal to k. That is important. So now if you look at 2-row immanent, normalized 2-row immanent, that is denoted by this, then what we are saying is there is this monotonic property. Yeah? So how do we show this? So if you want to compute normalized immanence, we don't compute it using the original definition. That is, we don't sum over all permutations and then take character value multiplied by some diagonal product and then sum this over all permutations. So we have this dual and alternative notion of vertex orientations. So for partition lambda and j, which is at most n by 2. So here I'll just say n by 2, but you have to be careful about floor, ceiling and all that, because all variables will be integers. So just for the sake of this talk, I'll just say n by 2, but I've written it precisely here. So denote by this chi lambda of j, the irreducible character chi lambda, evaluated at a permutation with cycle type 2 power j 1 power n minus 2j. So that's why you need 2 power j, so the j has to be an integer here. So for a tree T, let OI denote the set of vertex orientations with I bidirected arcs. So vertex orientation meaning you look at a vertex, it will choose one of its for every edge. Every vertex will choose among the degree of B, that means it will choose one orientation, one of the edges will be chosen. So now there are n vertices but only n minus 1 edges in a tree. So that means there has to be at least one arc which is bidirected, that is, there has to be at least one edge in which this endpoint chooses this edge and this endpoint also chooses this edge, the same edge. That means it's a bidirected arc. So in general, if you look at all possible orientations, there may be several bidirected arcs. So let OI be the set of all vertex orientations with exactly I bidirected arcs. So when I say with I bidirected, it's exactly. So what Mukesh and I did was that we showed that there exists a statistic, lexicographic array, whose ordinary generating function, that is, so you look at AIQT, which is sum over all orientations with I bidirected arcs, Q power this lexicographic array. This summation, that is one of the important components in computing the normalized immanence of the Q analog of the Laplacian of T. Yeah. So we will, if you look at our paper, we just say AIQ because there the T was not relevant. Here the T will be relevant, so I will change it to AIQ of T. So what we proved earlier was that if T is a tree on n vertices with Q Laplacian LQT. Lambda is a partition of n with normalized immanent d bar lambda LQT. And this d bar lambda LQT is, so 1 by this chi lambda of the identity permutation. We have this AITQ. So you remember this is the AITQ, which is what is defined. This is the polynomial with non-negative coefficients times some. You see, you get some alternate version. That is I choose j chi lambda of j. That is here your you have AITQ multiplied by something, which is and Chan and Lam showed that this quantity, binomial coefficient weighted character evaluation, this is non-negative for all lambda. That's what they said. So in fact, that shows that you can write it as a sum over of positive quantities. With AITQ, here except for A naught of Q will be the determinant is 1 minus Q squared. All other AIQ we have, it will be a polynomial with non-negative integer coefficients, and in fact it will be a polynomial in Q squared, not just Q. And you can multiply it by some positive quantity. So this actually gives you an alternate proof of Schur's theorem, which says that that the immanents are positive, that is non-negative. So if it is non-negative, you should be able to write it as a sum of non-negative quantities, and here is one way to write it as a sum of non-negative quantities. So, in fact, what Chan and Lam proved is that this binomial coefficient weighted character, this summation, that is actually 2 power I times something. So here, since j goes from 0 to I, this quantity is a power of like 2 power I times something. So 2 power I times something here. And then here we get this. All right. So I want to fix this number of n number of vertices, and I'm going to use this lemma. So this is true for all lambda partitions lambda. I'm going to instantiate it with 2 row partitions. So you change lambda equal to 2 row k. So let's note the character as 2 row chi. So this is just some notation. Yeah? So if you do the same thing, you will get 2 row immanent. The normalized immanent is 1 by the character value evaluated by the identity permutation times this AITQ 2 power I alpha n ki. This is just the same thing. All this third equation, I'm just doing the same thing, except that alpha n lambda I is called alpha n ki because it's a 2 row partition, the second part having k boxes. All right. So if you look at the few alpha n ki, you just look at the table. So what is our aim? Our aim is to show that this sum when something k, and if you look at the similar sum for k minus 1, then the sum for k is greater than the sum for k minus 1. That's what we want to show. So how do we show this? So let's see, this AITQ is always a non-negative integer except when I equal to 0. When I equal to 0, in fact, it will be 1. You can see alpha n ki. We'll see. And then, so if you can show that the alpha n ki is as k decreases, alpha n ki is greater than alpha n k minus 1 I divided, and we have to divide by this also. Then it will be good. So if you look at this, alpha n ki. So you look at this one. This seems to be the table of alpha n ki. So I is varying. I is the index variable for the rows. K is the index variable for the columns. So here k is 0. That's why I'm writing lambda. The partition is 6, 0. The 0 you will ignore. Here lambda is 5, 1, 4, 2, 3, 3, so on. You won't get 2, 4 because that is the same as 4, 2. It's a partition. First part is greater than or equal to the second. So if you look at this now, and if you look at the first row that follows from this, we look at alpha k0. So 2 power 0 is 1. So alpha k0. When I equal to 0, it will be 0 times chi lambda of 0. So 0 meaning you have 2 power the cycle type with evaluated at a permutation whose cycle type is 2 power j, 1 power n minus 2j. So it's 1 power, this is j 0, it's 2 power 0, 1 power n, which is the identity permutation. So this alpha n k 0 will be the character value of the evaluated at the identity permutation, which means this is the denominator. So this denominator is actually alpha n k0, alpha n lambda 0, which we are going to write as alpha n k0. So that's why this first row is written in red color. So that's the what is going to use to be the denominator term. So 1, 5, 9, 5, this is the denominator, 1, 6, 14, 14, denominator and on. So here you can notice a few relations. For example, if you look at alpha 5 2, no, when n equals 7, 5 2, this is 10. This is actually, so alpha n 5 2 is alpha 6 4 2 plus alpha 6 5 1. Because 4 plus 6 is 10. The 6 plus 3 is this 9. This 4 plus 2 is this 6. Yeah. Here and then that pattern continues. 7 plus 6 is 13. Yeah? If you look at some cell which is colored, then you look at the previous n and then look at two cells and you will get it. Except for this last column. So if you look at this last column, no? So 14 9 6 4. So 14 9 6 4 that comes. You can think of it as having a column of zeros here. That's why you add up, you will get 14 9 6 4. The only thing is here you will get one extra row. When n becomes even, you will get one extra row because this I will go up to n by 2. There you get one extra row. Yeah? So if you divide, no, this we are looking at this normalized immanent. So if you look at the alpha nki divided by this alpha nk0, that's what we want. If you look at that, you get 1 by 1. So for this 6, I'm trying to, so it will be 1 by 1, 5 by 5, 9 by 5, 5 by 5, 1 by 1, 4 by 5, 6 by 9, 3 by 5, and so on. 6 by 9, 3 by 5. So essentially I'm dividing by the entry here at the first. The first row entry is going to be used to divide that column. So very good, except that the last row when n equal to even is it doesn't come as a sum of the previous. So here, because there is no previous, so this last row cannot come by induction, because if you look at this, there is nothing corresponding to I equal to 4. So if you want to look at I equal to 2, 5 2, you get these two, 5 2 and 4 3. That will give you I equal to 2, 5 3. But if you look at I equal to 4, and if you want to go back, there is no I equal to 4 when n equal to 7. So when n equal to 8, this I equal to 4, this one extra last row will come. And that's how is it coming? It's not coming from n equal to 7. That one row is going to cause you some trouble. And the first row is the dimension of the irreducible, that's I've already said. And the difference of successive coefficients of the polynomial 1 plus x whole power 2n. This follows some standard. So we look at this 2-row normalized immanent for k and for k plus 1. And this 2 power I, ai, tq, they are common within the summation. So if we can show that these ratios, so what I'm doing is, I'm going to write it like this. ai, tk, 2 power I, alpha nki divided by this 2. So this fraction, I'm going to take it inside the summation. And I have the summation alpha nki divided by the alpha nk0 actually. Yeah, this. So this is same. So if we can prove this alpha nki by alpha nk0 is greater than or equal to alpha n k minus 1 I by alpha n k minus 1 0. Then we are done. Then it's decreasing. Then we can hope to do. All right. So this is what we want to do. So nk greater than nk plus 1 I by nk plus 1 0. All right. So this is our first lemma. It gives them this recurrence that we noticed that can actually be proved. This is using the Murray-Nakayama lemma and evaluating the character. So that gives you this. And we have another following easy lemma. If you have positive integers a, b, c, d, if you look at minimum of a by c, b by d, and maximum of a by c, b by d. So the a plus b by c plus d is between the minimum and the maximum. This is kind of easy to see. It's a standard inequality. So we are almost done. The only catch is that when n equal to 2l and I equal to l, so n equal to 2l is even and I equal to l. In that case, we get a new row, and this row is not obtained by induction from n minus 1, but you can obtain it by induction from n minus 2. So this last row, is obtained as a successive difference of coefficients of the polynomial. So this trinomial polynomial, which is 1 plus x square whole to the l. So in that, if you look at coefficients, you will get the difference 1, 6, 1, 3, 6, 6, 3. That will get as successive differences of coefficients of this polynomial. Yeah? And this is the entry point into the world of path commutator. This last row is what is going to cause us trouble. If it had not been for the last row, the proof is done using these two lemmas. These two lemmas will finish the proof, except for the case when n is even, which is 2l, and I equal to l. That is a case which is going to cause us a lot of trouble. So this For this, we have to do a lot of path combinatorics because of this successive differences of coefficients of this polynomial. Yeah? And yeah. So if you look at Riordan paths of length n, they are counted by these Riordan numbers. They are from paths from 0, 0 to n0, with steps being up, down, and horizontal, which don't go below the x-axis and have no horizontal steps at height 0. This is just the definition of Riordan numbers. And this is the Rn is known to be the difference between the central trinomial coefficient. This is the the middle coefficient, no? The largest. That is called the central trinomial coefficient. That and its predecessor, that is known to be the Riordan number. So, because of this, you see, this obtained the successive difference of coefficient of the polynomial. This tells us that the polynomial 1 plus x squared whole to the L is important. And if you look at differences of successive coefficients, so let's say pkl is the coefficient of x to the k in this, and pk minus 1l is the coefficient of x to the k minus 1 in this. So pkl minus pk minus 1l is important. That is what will give you a last row. So we have to use a couple of properties of Riordan numbers. So like log convexity, and some recursion, and so finally we are able to show that this satisfies this. That's the bottom line. Yeah. So now I'll come to this other question. So we have this fractional quantities in each row. They are all less than or equal to 1. So is there some RBC? If you look at this table, no, I'm just reproducing the table for n equal to 8. And the table for n equal to 6 is already there. So let me just do it for 8. So if you look at this, no, they're all fractions which are less than 1, less than equal to 1. Yeah? So the first row will be all 1s. And then if you look at C, what I'm trying to show is 1 is greater than 6 by 7, greater than 15 by 20, greater than 19 by 28, so on. Yeah? So all of these, they seem to be decreasing as you go from left to right on this table. So this will be 1, 1, 1, 1, 1. So you can say it's deeply decreasing. This 1 is greater than 6 by 7, greater than 15 by 20. So this is what we observe from the table. And if you prove this is good enough. So now this looks like, all the fractions are less than or equal to 1. So that means they seem to be probabilities of some events. So is there some event whose probability is 11 by 20, 15 by 20. And then, so that means there is some probabilistic way to maybe interpret this data, and then if there is a probabilistic way, there may be a probabilistic way to prove this. So that would be more interesting. So I can give you a probabilistic interpretation, but I don't have a probabilistic proof. So the algebraic proof gives you a probabilistic interpretation. Coupled with this probabilistic interpretation gives you some relation about this probability, which are decreasing from left to right. But can we get a probabilistic proof? That would be very interesting to get one. I would be very happy to see one. I don't have a proof yet, but I would be very happy to see. Okay, so let me just define. So our interpretation involves these generalized tick paths. So these are up-down non-negative paths from 0, 0 to n minus 2k. So having k up steps and n minus k up steps and k down steps. So up meaning you go 1, 1, that is, you start, all of them are starting, you have the lattice, you either go up and then you come down. So when you go up, you increase the x coordinate by 1, y coordinate by 1. If you go down, that means you increase the x coordinate by 1 but decrease the y coordinate by 1. So up step is from x by 2, x plus 1, y plus 1. Down step is from x by 2, x plus 1, y minus 1. Yeah, decrease. Okay, so I'll just consider the case when n equal to 12 is even. The interpretation will be the same for n equal to 12 plus 1. So our interpretation for alpha 2l ki, yeah, this fraction, alpha 2l ki, it will involve generalized dict path. So I'm looking at only the cardinality yet as of now. I'll then come to the probability interpretation. So it will involve generalized dict paths from 0, 0 to 2l minus 2k, because you see here n is just 2k. So n is just 2l, I'm sorry. So from 0, 0 to n, n minus 2k, it will become from 2l to 2l minus 2k. So we divide the 2l steps on the x-axis. So the path is from 0, 0 to 2l, something, 2k. But the number of steps is 2l. So we divide it into L intervals of length 2, that is like 0 to 2, 4, so on. Yeah. So we call this S1, S2, etc. Yeah. You look at this S1, S1, S2, S2. So we will permit, if you look at a path, no, there are a lot of these peaks in the path. So a peak is some coordinate such that you came to that point and then you went down. So that's why it looks like, if you look further, if you look at this, no, for example here. So here, this is a peak. This is a peak. These are peaks. So we're interested in peaks. We will permit peaks to be at only have an odd height at a point in xy in this interval. So you want to look at all peaks which have odd heights at restricted positions. That's what we want. Yeah. So with this notation, alpha 2L Ki, this is the cardinality of the set of generalized peak paths from 0, 0 to 2L, 2L minus 2K, with up steps, down steps, and odd peaks contained in the set D, L minus I. So here, if you look at alpha 2L K, so the 2L and K determine the length of the path and the number of up steps and down steps. What is this I? This I will tell you where odd peaks can appear. So because it's a path which involves only steps, up steps and down steps, if you look at if the x coordinate is odd, y coordinate will also be odd. If the x coordinate is even, y coordinate will also be even because of the definition of our path. The steps are only 1, 1 and 1 minus 1. So 1, 1 will go up, 1 minus 1 will go down for the reason. So that will tell you that the x coordinate and the y coordinate will have the same parity. Yeah? So if you look at a peak, its x coordinate or a y coordinate, both of them will have either be odd or will either be even. So the peaks of odd height can only be restricted. That's what this is. Yeah. So you get a similar, exactly the same. Only thing is for n equal to even, it's obvious. For n equal to odd, you have to do a little more work. So here there will be one extra up step. All these. So 2L minus K. Yeah. All right. So if you look at this data for n equal to 8, we get this. I will illustrate this last column. Yeah. See, lambda is 4, 4. So we have 4 up steps and 4 down steps. So here I would have 5 up steps and 3 down steps. For this column, I would look at some cardinality of paths with 5 up steps, 3 down steps, and with some peaks having odd height, having some restrictions, restricted peak with odd height. So here 4, 4 will be. Yeah? So this is fine. Let's try to get this. I will try to illustrate this. So see 3, 4, 6, it always keeps increasing. This we can show that it increases from bottom to top. So let me start with this 3. So these are all those Catalan paths. So from 0, 0 to 4, 4 will be Catalan paths. So this is a Catalan number, this is 14. And it will have no peaks at odd heights. 3 of them have no peaks. So if I use 4, that means it has no peak at odd height. So it has 3. So to fit this picture, I had to sort it by height of the path. So then I couldn't sort it by height. So I equal to 4. You see, there are these 1, 2, and 3. So all of these, if you look at the peaks, the height of the peak is 1, 2, 3, 4. It's the even height peak. So here height is 2. Here height is 2. So there are no odd height peaks at all. That is the paths in this 3. So what is this 4? You have an odd height peak, but only in the first 2. In this first 2. Later, after this, so now we are breaking it into 4 segments because I equal to 4. So breaking into 4 segments each of length 2. So the last row corresponds to those paths where there is no odd height peak at all. This penultimate row corresponds to those where the odd height peak is only at the first. Then what will be the second last row? It will be those paths which have odd height peaks only in the first 2 blocks of length 2. Then first 3 blocks of length 2. Then first 4. That's okay. So that gives us. So these 3 have no odd height peak at all. If you want to go to this 4 of 14. So how do you get 4? There is I equal to 3. So there is this path, see, which has a peak only in the first block. Odd height peak only in the first block. Nowhere else. Yeah. And then now you can see, I equal to 3. And I equal to 2, you will get 1, 2, 2 more. So then you get 6. Yeah. So here you have an odd height peak. So if you height of the peak is 3, it is odd. But it's only in the second block. So it will either be in the first block or the second block. union for 1 union 2. First block of length 2, second block of length 2. Only there in B. Okay. So this is our interpretation. So what is our probabilistic interpretation? So, and when you're dividing it by this total length of all paths. So, what is the interpretation for the fact that the alpha n case, the fractions keep decreasing as you go from left to right? What is the interpretation? So that says that 6 positive integer n and I less than n by 2. The probability of a non-negative UD path with n total steps and k odd height peaks contained in the set. The odd height peaks contained in the set 2n minus I decreases as the number k of down steps increases. Is it clear? So this is the interpretation we have for the main result that we have. The probabilistic interpretation involving peaks at odd heights. Now this is the alright. So and then you can change this into, use the language of standard Young tableau and transfer results into slightly different language. Alright, so if there are any questions, I would be happy to take.
Professor Arumugam.
So we shall wait for questions. Is the speaker available?
No, sir, he did not join us.
Okay, then we shall thank the speaker for his recorded delivery of the talk, and we close the session now.
Yeah, we understood that in the recorded this talk itself, there was some audio problem, some noise was coming.
Yeah, right.
We are sorry for it. We thought there could be some technical problem from our end, but it is not so. Somehow we did not capture that particular information. Anyway, it is done now, and we can proceed for. Anyway, now speaker is not here around, and he is not in a position to take up the question, but he will be here in the afternoon. He's supposed to be here. I don't know if there is any problem or not. So we will wind up this session. Thank you, Professor Armugam.
Thank you.
And Raksha, please take over.
Thank you, Professor Khare and Professor Shivaramakrishnan Sivasubramaniam for a wonderful session. I also thank Professor Arumugam for chairing this session. Thank you very much. Now we'll have a short break. Next session will be contributory talk. It will start at 11 IST. There will be parallel sessions which will take place in Professor T.E.S. Raghavan Sub Hall and Professor R.B. Bapat Sub Hall. Kindly join the respective links. And the afternoon session will start at 13:30 IST, which will take place in the same link, that is Professor C.R. Rao Hall. Thank you. See you soon.
Take care. Can you hear me, Raksha?
Yes, yes, sir. Yes.
I don't know that.
Hello, Professor Bapat. How are you?
Yeah, I'm fine. Thank you. Nice to see you. Yeah.
Yeah, nice to see you too. Yeah.
Raksha, we can start, I think. Would you like to make any announcement? Raksha?
Yes, sir. Yes. Can you hear me, sir?
Yeah, definitely.
Welcome back to the afternoon session. I request Professor Prasad to take over. Sir, please.
Good afternoon, everybody. Now we'll be having entire this afternoon. We'll be having sessions dedicated to our beloved Arvind Lal. Professor Arvind K. Lal, simply Lal for most of his senior friends and colleagues, or Lalda for younger friends and colleagues, is no more with us. He is remembered not only as a mathematician contributed to his area of expertise, he will be remembered as good student, good teacher, and good friend. He was a very active member in our organizing committees since the beginning of 2012. In his memory and to honor him, now we have a session dedicated to him, for which Sukantapati, Professor IIT Guwahati, is the organizer. I welcome Professor Sukanta to come forward and organize this session along with Lal's teacher, colleagues, friends, and students. Sukanta, please take over. Sukanta, are you with us?
Yes.
Yeah, please. You can advise Raksha to, in case you want to play recorded words, Raksha can be advised. So
Yeah, you mentioned some morning for 1 minute, right?
okay, then you declare the okay.
Yeah, we can, if we can observe, yeah, 1 minute morning for, like for Professor Lal, it will be good.
Yeah, Umashankar, please, whatever you prepared that can be kept during this period.
Okay. I have prepared a small presentation um, on Professor Arvind Lal. I request Raksha to kindly play that. Raksha, can you play that, please?
Yes, sir. Yes, give us a minute, sir. We'll play. Sorry for the delay. We will play the recording soon.
Sorry, Sukanta. My colleague misplaced the file,
Professor,
and he's just locating and bringing it in.
Professor Manjunath,
These things came
I'm
in the
still not
last minute,
presented.
all
Yeah.
mistakes occurring.
Right, Professor Manjunath, I'm still not a presenter. Please note that.
Raksha?
Yes, sir. Yes, we will make him present.
session in honor of Professor Arvind Lal. He was in honor of Professor Arvind Lal. He was born in 1966 in a village called Uttara in the district of Madhubani, Bihar. The parents, Srimati Susila Devi and Sri Leknaran Lal. He grew up with a brother and two sisters. Probably this is when he started developing the nature to care for others and understanding others. Later on, that nature would make him help many people in real life. This was his school days. He studied in the Sainik school in another village called Tilaiya, which is about 25 to 30 kilometers from his village, Uttara. He completed his school in 1983. He is the number 8 student sitting on the right. He completed BA Mathematics honors in 1986 from Hansraj College, Delhi. And then he did his MSTAT from ICLAA, Delhi. And after that, he did PhD in ICLAA, Delhi from 1988 to 1993 with the supervision of Professor Bapat. This is the place, ICLAA, Delhi is the place where he made many good friends, mostly due to his frank and free nature of talking, and also because he is a very sports loving person. After that, he visited TI for Mumbai for a year, where he worked on combinatorics, and then he visited HRI Allahabad for 2 years, where he worked on coding theory. Coding theory was his first research area. After visiting HRI Allahabad, he joined as a faculty the Department of Mathematics and Statistics, IIT Kanpur in 1996. He was an excellent teacher there. Many students would remember, even now they remember, how he would simply say, don't worry about the grade, just try to understand the subject. And he has also served IIT Kanpur in many administrative positions, head, dean, gymkhana, chairman of different things. Yeah. He got married in 1996 to Miss Niyati Padi. They have a son, ONS, and a daughter, Nilisa. ONS is now studying in Delhi, and Nilisa is studying in Hyderabad. As I said, coding theory was his first love. Many significant contributions he had there. Visited many places. in 2000 to 2001. During that period, he visited University of Puerto Rico to work with Professor H.L. Janua. His second research area, he was it was graphs and matrices. He was very active there. Many significant contributions, and plus he has helped popularizing the subject in the country in a big way, always helping, involved in organizing conferences or helping students all over India. Always doing that. And this photograph was taken during 2019 in a conference at ISI Delhi. The conference was in honor of Professor Babad, and some of the people who are present here also, present in the photograph, they are presenting in this conference also. You can see, and in the center you see Professor Babad and Professor Lal is there, and just in the back row behind Professor Lal, there is Arupda, who is a very close friend of Lalda. A very close friend of Lalda. I will try to take a minute to highlight one of his many significant contributions as simply as possible. Just look at the two pictures here. Whatever you understand from connectivity, you understand. Just try to tell with whatever understanding, which connectivity is bad. Maybe I should give the sense. What you do is like you insert a central point in both of them and try to rotate. Which one would break first? Then you will get a feeling that the left one will break first. And that was captured by one of his articles when these cycles were actual cycles, event cycles of graphs. And it was proved that the left picture will have a smaller algebraic connectivity. So algebraic connectivity is a term in like the spectral graph theory. It's the second smallest eigenvalue. Smallest is 0, the second smallest eigenvalue of the Laplacian matrix of a connected graph. He worked on that. And yeah, this was very and this was a significant contribution. And even in this conference, we had a talk. I think Devajit presented a talk, which based on, which took the theory even forward. People, motivated on with this work. People are working, motivated by this work. Always very happy, a very hearty laugh, and the words "Khush raho," they are the eternal words that will always echo in our hearts forever. Even now also, we feel your presence. Thank you. Now I request Professor Bapat to take over and start the next session.
Okay, so we will continue the technical part. I think we are just about 5 minutes behind, but that shouldn't matter. We will adjust it. So,
Laksha, there is one thing.
Yeah.
He preferred to give a live talk if possible. So only if situation demands, we'll go for his recorded version. Okay.
So we'll start at the live talk.
Yeah, he prefer to give that. Let him try.
Okay, so the first speaker of this session is Professor. So should I start, or is there some introduction?
Please.
Yeah. So the first speaker is Professor Tirthankar Bhattacharya from the Indian Institute of Science, Bangalore, and he will give a talk on commuting isometries. So please, Professor, over to Tirthankar.
Yeah. Thank you, Professor Bapat, and thank you, Professor Manjunath Prasad, for inviting me to this very memorable occasion, of course. And yeah, okay, let me start the presentation. Can you see a PowerPoint presentation?
Yes.
Is it full screen now?
Yes.
Yeah, I'm very thankful to the organizers for inviting me to this, because this gives me an opportunity to remember my friend Lal. He was always called Lal by many of us. His full name was Arvind Kumar Lal. As Shukantapati already informed you, he was born in 1966, in fact, on the 1st of January. We met him at ISI Hostel, ISI Delhi Hostel, as Shukantapati also said. Lal came there after his bachelor's in mathematics from Delhi University. He came to ISI in 1986, finished MStat in 1988, and joined Professor Bapat. I arrived at the ICLAA hostel in mid-1989 because for doing the second year of MStat. It was possible to do the first year at Kolkata and the second year of MStat at Delhi or somewhere else, depending on the specialization. So we met Lal at that time. Right from the beginning, he was always like an elder brother to many of us. What one immediately noticed, more or less, within a few interactions, is he was always very fair and selfless. So his presence in any environment, in particular at ISI Delhi Hostel, was always like that. I'll recall. So we of course kept in touch, and he finished in 93 and left. I finished sometime after that. I'll recall an incident. It was late 1995, I think, or early 1996. We were going to Guwahati. For some reason, Lal and I. Lal was coming from Allahabad, and I took the train from Kolkata. I probably had gone home for some reason. I took Kanchenjunga Express, and there was a derailment or something like that somewhere in North India. Consequently, all trains, many trains were disrupted. Kanchenjunga Express was chock-a-block. I knew Lal's train was cancelled, and he knew I would be traveling that day. These were pre-mobile days. I anticipated him, and he did exactly what I anticipated. He came to Kishanganj and took Kanchenjunga from there. In those pre-mobile days, in the crowded train, he searched for me and eventually found me. I had a berth to myself, but that's all. As you can imagine, and there were way more people than who had reservations. And so we were very glad to find each other. There was a young family with a young child traveling. And but there was a family with a young child traveling. They had the side berth to them, and 3-4 young ruffians were troubling them. This was fun for these ruffians and extremely a big nuisance for the family. So I could see Lal fuming inside. At some point, these young troublemakers crossed a line, and they probably threw out a belonging of the family out of the window. This was a sleeper class train. It was a bar of soap. They were traveling with a kid, so cleanliness was important. They had a bar of soap. And now Lal couldn't take it anymore. He started fisticuff, punching them, took them by the collar and said, "Why did you do this?" I was kind of taken aback. But of course, since Lal was fighting, I had to join in. So we fought. We were outnumbered. Nevertheless, we won. I mean, basically because well, honesty and straightforwardness wins. Probably that is they apologized. But I'm recalling this because this embodies him. He in a given situation, if he sees unfairness, he has to respond to it. This is independent of his own gain or loss, the risk involved, whatever. If there is unfairness in the system, he cannot keep quiet. This theme, this continued all the while. That's why this incident is etched in my memory. We often met after I finished PhD, and well, he joined IIT Kanpur, I joined ISC. We often met at some meeting or other. Lal was always his jovial self, and he was a great team member in a meeting. If we found ourselves arguing for the same cause, then it was greatly beneficial to have him. He was a strong man. He wouldn't let anyone get by. If the meetings happened to be at IIT Kanpur, he played an excellent host. We shall all miss him dearly. As you know, whom the God loves die young. And we'll probably agree that death has been kind to him. He had a painless death, which also, of course, people who the God loves, they die painless death. And we shall all remember him for long times to come. I shall kind of now shift to the technical part. I have to. Right. Can everyone see the new file, the PDF?
Yes.
Okay. Someone stopped me after, Professor Bapat stopped me after 30 minutes or 35 minutes, something like that. I mean, yeah. Yeah. So I'll talk on a commuting pair of isometries. Old theme, extremely old theme. This is a new piece of joint work with a student of mine called Shubham Rastogi and a postdoctoral fellow, U. Vijay Kumar. We start with the Hardy space of the unit disk. First of all, in finite dimension, all isometries are unitaries because of the rank nullity theorem. There is no genuine isometry, meaning there is no isometry which is not unitary. So whatever I say will make sense only in infinite dimensions. The model space for this thing, that is the most loved space by functionalists when they do infinite dimensional analysis, is the so-called Hardy space. It's a space of vector valued analytic functions. The vector valued meaning, well, sometimes the vector valued could be just complex valued. It's good enough to think of just complex valued. So the script E that I have could just be complex numbers, or could be a Hilbert space as well. Analytic functions have Taylor series expansion, and the space consists of just those functions whose Taylor coefficients are square summable. If E, the script E is equal to C, I shall simply denote it by H2D. And H2DE is identifiable in a very natural way with H2D tensor E, the Hilbert space tensor product of two Hilbert spaces, H2 and E. On this, we have one natural bounded operator, namely multiply by Z. So you can think of it in these two avatars, whether E valued H2 or H2 tensor E, you can think of it accordingly think of the operator in two avatars. One is just multiplication by Z, that's on H2DE. The other is MZ tensor identity E, where the simple MZ without a superscript E is MZ on the scalar valued H2. Okay, this is an isometry and it's not a unitary. In fact, I mean, it fails to be unitary by a little bit. Given an isometry, the defect operator is, this is just a notation. if V is an isometry, VB star is a projection, that's easy to see. And the orthogonal projection I minus VB star is denoted by dV star. An isometry is said to be pure if V star power n, there's a typo here, I'm sorry. V star power n x goes to 0 for all x in the Hilbert space H. So in other words, V star power n goes strongly to 0. Now why make such conditions? Are there examples? Indeed, yes. MZ itself is an example. And there is an abstract characterization, that is, an isometry is pure if and only if it is unitarily equivalent to MZ, may be multiplied with a multiplicity, tensored with a multiplicity. Now the great theorem, which with umpteen number of applications and which makes the study of isometry really very down to earth, is by Wald. So Wald said that take any isometry. First of all, it could be a unitary. Unitaries are isometries as well, special isometries. So Wald said that the whole space, well, up to unitary equivalence, all the time up to unitary equivalence, the whole space breaks into a direct sum of two parts of reducing subspaces. The whole space breaks into a direct sum of two subspaces, both of which reduce V. And on one of these reducing subspaces, V is a unitary, that's the lower right corner W. And on the other one, it's the shift, maybe with a multiplicity. Sorry, again a typo. This ID should really be IE for some E. I mean, D can also be thought of as a space, but one should have been consistent with the notation. So a given isometry V is always unitarily equivalent to just a unitary direct sum MZ with some multiplicity. So apart from unitary, the only other genuine isometry is MZ, which is sometimes called the shift. And any isometry is a direct sum of these two things. There is no other isometry. Now, as I said, there's an umpteen number of applications, but one application which is immediate is that if you take an isometry which is not a unitary, so if an isometry is a unitary, its spectrum is contained in the unit circle. Every unitary has spectrum contained in the unit circle. From small to big, I mean, it could be very small and it could be the full circle, but it's contained in the unit circle. But an isometry which is not a unitary, its spectrum is the full closed disk, simply because that MZ part has to be present. And the moment the MZ part is present, the spectrum of MZ is the full unit disk. So this D, blackboard bold, D stands for all Z in complex numbers such that mod Z less than 1. D closure is mod Z less than equal to 1. Okay, so this issue is pretty simple for a single isometry. It's vastly different if you have two commuting isometries. So that's what the theme of the talk is. What is the spectrum of a pair of commuting isometries? Of course, for that, I'll first have to tell you what is the spectrum for a commuting pair of operators. I mean, we know spectrum of a single operator. Yeah, any question? Okay, I exited the full screen mode because there is a bit of a handwritten part and it was getting too small. Oops, sorry. Right. The joint spectrum of a commuting pair goes through for a commuting tuple, but I'll only be concerned with a commuting pair. The joint spectrum of a commuting pair. Now, before I throw the definition at you, which will be very, very which will look strange without the motivation. Note that if you have a single T, then T is invertible if and only if it is 1, 1 and on 2. Now, this can be written in a more fashionable way, namely you consider what's called a complex. And so here is the Hilbert space in the middle, H and H, and on the left there is a 0, on the right there is a 0. There are natural maps. The map delta 0 sends 0 to 0. The map delta 1 sends H to TH. Delta 2 sends all of H to 0. Now, T is 1, 1 and on 2 is the same as saying that kernel delta 1 equal to range delta naught and kernel delta 2 equal to range delta 1. The maps are so reduced that range of a map is always contained in the kernel of the next map. And if they're actually equal, then that's the same as T1, 1 and on 2. So I could say that T is invertible if and only if these range kernel conditions are satisfied. In short, the complex is called exact. So taking Q from here, Joseph Taylor defined a pair, actually again a tuple, but I'll stick to a pair. Pair T1, T2 to be non-singular or invertible if this complex is exact, the one written in the middle now. 0 to H, H to H direct sum H direct sum H to H, and then finally 0. The maps are delta 0 sends 0 to 0, delta 1 sends H to T1H, T2H, delta 2 sends H1H to T2H1 minus T1H2, and delta 3 sends everything to 0. Again, note that the way the maps are constructed, range of a map is always contained in the kernel of the next map. And so you say that the pair is non-singular if the sequence is exact, and you say that lambda 1, lambda 2 is in the Taylor joint spectrum if the complex corresponding to the pair of commuting boundary operators T1 minus lambda 1i and T2 minus lambda 2i, if this is singular. Now that's pretty abstract and not easy to deal with, especially the middle part. The end portions are somewhat easier to deal with, but the middle part is pretty non-trivial to deal with. Okay, a property we shall again there are many properties. This was a success when Taylor introduced it. It produces a compact subset of C2. It carries a homomorphic functional calculus. Something that I shall use very often is the so-called polynomial spectral mapping theorem. It says that if you have a polynomial P in two variables and you look at the spectrum of P T1, T2, T1 and T2 are commuting, so you can plug in and get P T1, T2. Spectrum of P T1, T2 is P applied on the set sigma T1, T2. Okay. Okay. The first example of a commuting pair of isometries comes from the Hardy space on the so-called bidisk, that is D cross D. So again, the same kind of definitions, all analytic functions, such that the Taylor coefficients, this time in two variables, is square summable. Taylor coefficients are square summable. And again, you could consider vector valued ones. Suppose mz1 and mz2 are the multiplications by the coordinate functions. They are commuting, they are isometries. The first example of isometries. One should start by asking, what is the joint spectrum of this pair? And turns out the joint spectrum is the whole bidisk. In fact, so for a pair of commuting isometries, due to a general property of the joint spectrum, the joint spectrum could not be bigger than the closed bidisk. They will have to be contained in the closed bidisk all the time. And for this pair, it is the whole closed bidisk. The argument is the same as why the joint spectrum of MZ is in fact the whole disk. The same kind of thing. So for this pair, sigma mz1 mz2 is the whole closed bidisk. If you consider such a thing on the one variable Hardy space, so mz tensor identity and mz tensor w is some unitary, then this spectrum can be calculated to be this: z times 1 comma alpha. Z comes from D closure and alpha comes from sigma w. So note that this is very small. In particular, if w is finite dimensional, this is just embedding of finitely many disks into bidisk, which is really, really small. So the spectrum can be as big as the full bidisk, can be as small as what is shown in the lemma. Another example. On the Hardy space of the bidisk, consider mz1 and mz1z2. Again, applying this polynomial spectral mapping theorem, you will be able to calculate the spectrum without too much difficulty. It turns out to be all elements of the form Z1, Z1, Z2, so that Z1, Z1 and Z2 are in D-closure. This is neither very small nor very big. For example, it has measure pi square by 2. So the point of giving these three examples is that all kinds of possibilities exist. Unlike spectrum of one isometry, there are all kinds of possibilities. The spectrum could be whole set, the spectrum could be small, spectrum could be somewhere in the middle. Possibilities exist in this case. Okay, any questions so far? Am I clearly audible and the slides visible?
Yes.
Okay. This is an old topic, as I said, has been studied by many people. I have listed some here. I'm sorry if I have forgotten some names. So many people have worked on this. One of the early results of Sochinski is the following. So if you have a doubly commuting pair, that is V1, V2 not only commute, but V1 star commutes with V2, then there is a wall type decomposition of the whole space. It breaks into 4 parts. So where on the first part, this HPP means, so these are reducing subspaces, and on the first part, both V1 and V2 turn out to be pure. That means they're essentially MZ tensor identity for something, for some identities. On the second part, the first one is pure, the second one is a unitary, third part just the other way, and on the fourth part, both are unitaries. So this is more or less a satisfactory analog of wall decomposition, but the conditions are very stringent that they are doubly commuting. Okay, a result that we shall be using for the new results that we are going to describe is something called the Burger-Coburn-Lebo theorem. So start with a commuting pair of isometries. Burger, Coburn and Lebo had this beautiful idea, which when you see, you think, oh, why could I not come up with it? It's very simple and elegant. Namely, start with V1 and V2, a pair, commuting isometries, take their product. So you get an isometry and take wall decomposition of that product. So the space breaks as HP direct sum HU, where on the HP part, the product is pure, and HU part, the product is unitary. And they turn out to be reducing subspaces for V1 and V2. On the second part, both V1 and V2 are unitaries. So that's the bottom right hand corner here where I'm hovering the cursor. On the first part, V1 and V2 are multiplication by some functions, operator valued functions. So the first part is really H2 tensored with, scalar H2 tensored with some E. And there V1 is M phi 1, V2 is M phi 2, and phi 1 and phi 2 are pretty simple. They have a constant term, then they have a linear term, and that's it. So U is a unitary, P is a projection. Phi 1 and phi 2 look like this for some unitary and for some projection. So this is a remarkable result about a pair of commuting isometries. The triple, the space E, the projection P, and the unitary U is sometimes called the BCL triple, the Burger-Coburn-Lebo triple for the pair V1 V2. Okay. The last thing that I shall need as a background is something that is somewhat recent. Go and Young introduced something called a defect operator. Like I introduced the defect operator for a single isometry. This is, as is written here, it turns out to be, in fact, a difference of 2 projections. For a single isometry, it was 1 projection. Here, it's a difference of 2 projections. This is a tool. It doesn't solve all the questions. It solves some questions. But there are things which cannot be handled with this so far. Okay. Okay. The first thing to note is there is a characterization of doubly commuting. So if V1 and V2 are doubly commuting, that is Sochinski's case, where he had a nice wall type decomposition. That's if and only if the defect operator is positive. So that's something to note. That's number one. Number two, we will come back to the positive defect case. But if the defect operator turns out to be 0, then it's pretty easy to see that the pair has to be like this. This MZ tensor identity and then identity tensor a unitary. That in fact is all. So this is a prototypical example. So, and in this case, the joint spectrum turns out to be D-closure cross sigma W. Again, note that the spectrum of the unitary W. Again, note that this could be very small. In particular, I mean, this depends on how big the spectrum of W is. If spectrum of W is small, it's just embedding of so many disks inside the bidisk. I'll probably skip this. Yeah. So this is a complete structure of the defect 0 case. So if you start with a pair of commuting isometries with 0 defect, then they have to be like this. So the space breaks into 3 parts. On one part it is MZ tensor identity tensor a unitary. On the second part it's just the opposite of that. That identity tensor unitary comes to the first part and MZ goes to the second part. The third part is commuting unitaries. I mean, commuting unitaries obviously have defect 0 by the definition of the defect. So this is complete characterization of the defect 0 case. Nothing more needs to be said. And consequently, since you know that joint spectrum of, for example, the first components, so you know the joint spectrum of the whole thing. Okay. The most interesting thing is the negative defect. This is a strange unitary that I'm defining on Hardy space of the bidisk. I won't go into how we arrived at this. But this is a unitary. This is a unitary which in fact commutes with multiplication by Z1, Z2. Consider tau1 equal to U star MZ1 and tau2 equal to MZ2U. So tau1 and tau2 are products of a unitary and an isometry. Consequently, they're isometries. They're commuting isometries precisely because U commutes with MZ1, MZ2. U commutes with MZ1, Z2. Turns out that tau1 and tau2 have negative, the pair tau1, tau2 have negative defect. Yeah, well, this is just to show how one computes the defect. It can be computed and has negative defect. We computed the joint spectrum of this, and in this case, actually the middle term had to be handled. The end terms were not of much help, and well, I won't go into the details of this computation, but turned out that this is actually, the joint spectrum is actually again the full closed bidisk. So this is a structure, a complete structure in the negative defect case. So if you start with a pair of commuting isometries such that the defect is negative, and then you take out the 0 defect part. That's what is occurring in the bottom right corner. If you take out the 0 defect part, so a reducing subspace where the defect is 0, if you take out that part, what remains is just tau1, tau2 with some multiplicity. Tau1 tensor identity, tau2 tensor the same identity. So it's acting on H2D2 tensor L. So tau1 and tau2 are prototypical examples. So this is like a Wald decomposition, just like Wald said that from an isometry, if you take out the unitary part, what remains for you is just the shift tensored with identity. This is exactly that. And so consequently, spectrum of V1, V2 in the negative defect case is full D2 closure. We saw that in the 0 defect case, it could be small. In the negative defect case is the full D2 closure. Maybe I'll skip these parts. I'll come back to the positive defect. Okay, so if positive defect, if CV1, V2, the defect is positive, then what happens is then also a Wald type decomposition is available. Again, you take out the 0 defect part, which can always be there. But modulo that, it's just MZ1 and MZ2 tensor with some identity. So MZ1, MZ2 on hard space of the bidisk is the prototypical example of a pair of commuting isometries with positive defect. Anything with positive defect is a zero defect part, direct sum MZ1, MZ2 with some multiplicity. So in this case also the joint spectrum is the full closed bidisk. So far what we have done is we have considered the defect operator, considered three cases when the defect operator is 0. A structure theorem gives the joint spectrum. It's positive, a structure theorem gives the joint spectrum, and when it's negative, then also a structure theorem and consequently the joint spectrum. Okay. Now for this pair of for all of them actually, you can write down the BCL triple. So the space, the projection, and the unitary can be written down explicitly for such pairs of isometries. Okay, how much time do I have left?
10 minutes.
10 minutes. Okay. So, okay, there are some more cases. Take two commuting isometries with whose ranges are equal. So consider, for example, example will be this kind of a thing: hard space on hard space tensor L, MZ tensor identity, and then MZ tensor W, where W is an arbitrary unitary on L. So the following things are equivalent. The ranges are same. Well, in terms of V1 kernel V2 star equal to V2 kernel V1 star. The defect. So why it's interesting is, so I said that the defect operator, the way it is written, it's a difference of two projections, but in this case it is a difference of two mutually orthogonal projections. That's not the case in general. So kernel V star actually breaks as the direct sum of two mutually orthogonal projections, and P1 minus P2 is C V1 V2. Okay. There is a characterization in terms of the Berger-Coburn-Lebo theorem as well. And consequently, you can write this down. This was also known, so due to Budak, you can write the whole space breaks as, so when range V1 equal to range V2, the whole space breaks as the H2 tensor L, ordinary H2 in one variable, H2 tensor L, direct sum K, and the operators have to be of the form that is written. Okay. Okay, so this is again a structure theorem which was known. There is a corollary that if V1 V2 are a pair of commuting isometries with range V1 equal to range V2, and so if V1 V2 is pure, the product is pure, then both V1 and V2 are pure. If you know a structure theorem, then you can deduce a lot of stuff. Okay. Range V2 contained in range V1 is kind of interesting because then V2 factors as a product of V1 and something else and some other isometry. So because of that, so V2 becomes equal to V1 V3, and because of that, well, this is an example. Again, I won't probably go into that. I'll just go into the joint spectrum result. So in this case, the joint spectrum is contained in Z1, Z1, Z2. You remember we had an example right towards the beginning where the joint spectrum was just what is written on the right hand side. And if range V2 is contained in range V1, then the joint spectrum of V1, V2 is always contained in this set. This is new. I mean, Budak had studied this, but nobody had studied the joint spectrum before. I mean, yeah, only small proofs can be given perhaps, and here is a proof for this this result. It's kind of straightforward. Okay. Here is an interesting example. So consider mz power m and mz power n. So m less than n, as you can see, one of them, the bigger one, is a product of the smaller one and another isometry. So here is an example where the inequality actually strictly holds. That is the joint spectrum result that I showed in the previous page. That can actually be a proper containment. The spectrum of mz power m, mz power n in this case is actually, so the containment in the last lemma can actually be proper, shown by this result. So very simple examples. Okay, I think here is something that I shall end with. Now, this requires a little bit of an explanation. So start with a pure pair of commuting isometries. So pure, the word pure here means that you have a pair of commuting isometries, and when you take the product, v equal to v1, v2, that product is pure. Now, what happens in this case is, maybe I should go back to the Burger-Coburn-Lebo slide for a minute. Bear with me for a minute. So I'm considering a pair v1, v2 for which the product is pure. And remember that the way H was decomposed was according to whole decomposition of the product. So if the product is pure, then the unitary part is not there, just not there. So H is equal to HP, and then that means that V1, V2 are just M phi 1, M phi 2 on HP. HP is H2D tensor E. So on that, V1 and V2 are just multiplication by these particular functions, phi 1 and phi 2. So if you start with something like that, now note that what's happening is V1, V2 is a pair of commuting isometries. So one can talk of the joint spectrum. At the same time, look at these functions, phi 1 and phi 2. So for every fixed z, phi 1z is an operator, phi 2z is an operator, and they actually commute. In fact, their product is z times identity, whichever way you multiply. So they are commuting boundary operators as well. So one can talk of their joint spectrum too. So on one hand, one can talk of the joint spectrum of the pair V1, V2, which is M phi 1, M phi 2. So joint spectrum of M phi 1, M phi 2. On the other hand, one can, for every fixed z, one can talk of the joint spectrum of the pair of commuting boundary operators phi 1z and phi 2z. So this result, the last result, is about that. Yeah. So pure pair of commuting isometries, let E, P, U be the BCL triple, which basically, okay. And so, which means that Vi is multiplication by phi I on H2 tensor E, where phi I are those functions that I wrote down with the help of P and U. P is a projection, U is a unitary. And phi I always look like that. That is what Burger-Coburn-Lebo proved. Then in several cases, what is true is the spectrum of V1, V2 is actually, you take union of the joint spectra of phi 1z, phi 2z. For every fixed z, look at the spectrum of phi 1z and phi 2z. That's a subset of the bidisk. Take union over all of them, that is z belonging to D. Closure of that, joint spectrum is always a closed set. Closure of that is spectrum of V1, V2. I think I'll kind of, it's 2:29, so I'll kind of end there. The talk is based on the first listed reference, which is on archive now. And anyone who is interested in these things, look at several papers of Burdak and Gasper. Burdak and his collaborators, Gasper and his collaborators, of course, Burger-Coburn-Lebo, Rongbi Yang and his collaborators, Jaydev Sarkar and his collaborators, and Popovici. Sachinsky is a classical reference. He has written after that as well a lot of stuff on these things. And yeah, so that's about it. Thank you very much.
Okay. Yeah, thank you, Tirthankar. So, are there any questions or comments from the audience? Okay, so yeah, if not, then let's thank Tirthankar again, and we'll thank you. We'll move on to the next talk, which is by Professor Nandini Nilkantan from IIT Kanpur, and she will talk about complexes from graphs. Yeah, over to you.
Thank you, Professor Bapat. And I would also like to thank Professor Prasad and Professor Pati for giving me this opportunity to present, to talk about some work. I have already given a recorded talk, but I would just like to take a couple of minutes to just remember Arvind again. And I think I'm one of these very fortunate people who did get to spend a substantial amount of time with him. And as I was listening to various people recalling their experiences with Arvind, my mind went back to the last day, the day on which he had that terrible heart attack. And we were supposed to meet for a discussion on that day, and he hadn't come till 11:30, at which point Shanmugraj and I decided to go and have tea. And three of us used to typically have tea together. And so as we were leaving, Arvind came in the opposite direction. And it was just, even today, I find it impossible to believe that in about half an hour after that, he had such a massive heart attack. So he just said that, okay, you people go ahead. I'll just come by. And he had a student with him. So he said, I'll just talk to the student and I'll come and meet you all. And at that point, I had asked, okay, we'll buy tea for you. And for the first time, Arvind said, no, I don't want tea. And we were both a little surprised, but we didn't pay much attention to it because Arvind never, ever said no to tea. And then we had tea, and Arvind apparently came to the canteen. We were sitting on the other side, and that's where he had his heart attack. And then we didn't know. We came back to the office, and when I came back and I saw his door locked, I was totally surprised because his office is just opposite mine. And then I called up his phone, and I'm without even bothering to say hello, I said, "Kahan ho tum?" And then the security guard answered and told me that, "Madam, unko to heart attack ho gaya." And that's when the world literally turned on its axis, and it was, I mean, then it was just terrible. On one side, one can feel very grateful for having had such a generous, I mean, he was a brilliant mathematician, he had a very brilliant, sharp mind, all of that. But today, I think when I look back, what I recall most is, or what I'm most grateful for is the fact that, I mean, I was around such a kind and such a generous person, and who was such a genuine person who never said anything bad about anybody, and who would constantly keep telling us, come on, khush raho, or don't take all these things seriously, everything will go. So there is, so the talk that I've prepared today is largely keeping Arvind in mind, because in the last couple of months, he was trying to learn a lot of algebraic topology, and we were trying to look at problems and we were trying to find some kind of a, okay, we were trying to see if we could see whether Laplacian integrable graphs were the complexes, we could associate certain complexes to them, which wherein we could say something about Laplacian integrability based on perhaps the homotopy properties of the complex and what. So though it is known that chordal graphs, the independence complexes of chordal graphs are vertex shellable, we were trying to study those. So the talk will not really be, it should be understood. If there are lots of students here, it will be very understandable to them. I have just talked about how you can construct a simplicial complex, and I've discussed the Neser conjecture in particular in the talk. And I've also just given an indication of home complexes and what kind of research problems they can lead to. And Arvind we were particularly interested in looking at chordal graphs, especially two trees, and to see whether there was some kind of connection between the Laplace integrability and in many cases, we were and whether if the independence complexes were not contractible, whether there was a connection between the integrability, Laplace integrability and that. So I would like to request the organizers to play the video. And thank you once again. And Professor Bapat, if it crosses the time, please feel free to cut the video at that point. Thank you.
Yeah, okay.
So I'd like to thank the organizers, especially Mr. for inviting me to do this talk in memory of my good and friend, Professor Algebra. Before I start my talk, I would just like to remember Arjun, who was very close to me and me. During the last 1 year of his life, we were both working together. I'm a topologist and we were both trying to study some graph theoretical problems, and we were trying to study it from the topological viewpoint. And it was
there is lot of disturbance. Lot of disturbance. I think some mic is on or something like that. There's too much of disturbance. You can try to play again with something. Something is on somewhere.
Yes, sir.
talk, I would just like to So I'd like to thank the organizers, especially Professor Pati, for inviting me to give this talk in memory of my colleague and friend, Professor Arvind Lal. Before I start my talk, I would just like to remember Arvind, who was a very close friend and a colleague. During the last 1 year of his life, we were both working together. I'm a topologist, and we were both trying to study some graph theoretical problems, and we were trying to study it from the topological viewpoint. And it was an extremely personal loss, in the sense that I not only lost a colleague and a collaborator, but I also lost a friend. And since I'm also very friendly with his family, we all feel his loss very keenly, both in the department and outside. He was an extremely, as a mathematician, of course, he needs no introduction in in this conference, because he used to go there every year and present his work. Definitely a very, very talented mathematician. And we also remember him as being an extremely kind and very cooperative person, in the sense that at least in IIT Kanpur, it was such that if something needed to be done, one of the first people you would think of approaching was Arvind, because Arvind almost never said no. And if there's a course for whom you could not find an instructor, numerous heads had probably approached Arvind to teach that particular course. And even if it was well outside his domain, he would take every effort to ensure that he could teach that course, and very approachable to students, very approachable to anybody, always available to help people out. And it's with a lot of sadness that one is giving this talk, because I really wish he were here and it was possible to be working with him and to be discussing with him. So I'm going to talk about something he was interested in towards in the last phase of his career. So we were actually trying to look at certain problems in graph theory. And we were trying to see if we could find some kind of an association between certain graph theoretical concepts and then we tried to associate a complex to it, a simplicial complex. And we tried to see whether some topological properties we could relate based on what topological properties we had. I'm not going to talk about that. I'll just try to highlight it towards the end of my lecture because it's not really written up at this stage. But so the title of my talks will be Graphs and Simplicial Complexes. So there are several ways to analyze the topology of a graph. So before I will start with a standard graph theoretical problem. I will also give an idea about how this area evolved through the work of Lovász when he was trying to prove a particular conjecture proposed by Naser. And then I'll just show the progression towards some topological aspects, and I'll try to finish it off with what is called the independence complex. So one possible way to study the topology of a graph will be to build up a suitable abstract simplicial complex from this graph, and then try to use tools from algebraic topology. So the resulting complex, the analysis when we try to study of the resulting complex can give a lot of topological insights into the actual graph, the considered graph. So today what I will do is I will start with this the problem, a very classical problem in graph theory, that is trying to determine the chromatic number. So given a graph G with n vertices, so the cardinality of the vertex set of G is n, how many colors are required so that the vertices can be colored in such a way that any two adjacent vertices receive different colors. So one can just take a simple example here. For example, let's just take the complete graph on 4 vertices. Clearly in this case, if we color this red, then I can color this yellow, this perhaps green, and I will have to use a fourth color here. So this I would color blue. So we also know that the minimum, we can't do with less than 4 colors over here. So the minimum number of colors required to color the graph is called the chromatic number of the graph. So typically for a graph, we would denote the chromatic number to be chi of G. And chi of G is usually this is rather hard to compute. And it's also NP hard, even in trying to determine all graphs with chromatic number, for example, 3, would not be very easy. And one can see that this is exactly the minimum of the set of all n, such that there exists a group homomorphism F from G to, a graph homomorphism from G to the complete graph Kn. So this idea of using simplicial complexes to address problems in graph theory is, this was proposed by Lovász in 1978, and he used it to prove what is called the Naser conjecture. So before I state the Naser conjecture, I'll give the definition of a Naser graph with a couple of examples. So let's start with the set consisting of 2nk plus 1 elements, which one can also denote this way. So any subset, since we want to describe the Naser graph, the notation will be kg and k. So we need to first determine what the vertices will be and which two vertices will be adjacent to each other. So any subset, say V of x, is called a vertex if the size of V is n. Okay. Suppose we take two vertices V1, V2 belonging to the vertex set, that is both these are sets of size n, then we say that V1 is adjacent to V2 or V1, V2 belongs to the X set of the Naser graph if and only if V1 intersection V2 is empty. They have trivial intersection. So one of the standard examples is the Peterson graph. KG21. So here let us take X to denote the set 1, 2, 3, 4, 5. So the vertex set here will be n is 2. So it will be this all the two sets of size 2, which I will just denote this way. 1, 2, 1, 3, 1, 4, 1, 5. 2, 3, 2, 4, 2, 5. 3, 4, 3, 5, and 4, 5. There'll be 10 of them. And the graph will look this way. So 1, 2, 2, 5, 3, 5, 3, 4, 1, 4, 2, 3, 4, 5, 1, 3, 2, 4, 1, 5. So let's try to color this. So if we color this red, neither of these two people can be red, so one can choose red over here. So which means one is automatically forced to choose a different color, blue here. Since this is connected to both these but not to this, again one can choose blue here. But this person is connected to both these, so I'll have to choose a different color. So let me choose green here. So similarly, you can continue and try to finish the outer portion also. So okay, let me just do it. So let me put this to be green. This I can't choose green. So which means here I will have to choose a different color. Let me go with blue. So this is connected to green and this, I can use a red over here. So here I can go with a green. And in this case, I can go with a red. So here what we notice is that chromatic number of the Peterson graph KG21 is equal to 3. Now 3, for us K is, I'll just make another observation here. This is K plus 2 because in this case here, what we notice is n is equal to 2 and k is equal to 1. Since the chromatic number here is 3, so what I have is I have chromatic number of kg21 is k plus 2, which is 3. So the question is, in general, can one actually make a statement about the chromatic number of the Naser graph? In fact, you can. This was proposed by Martin Naser in a totally different setup. But what the Naser conjecture said was essentially this. The chromatic number of the Naser graph kg and k is equal to k plus 2. I'll just spend about a couple of minutes here talking about this particular graph and getting the bounds before I introduce Loise's statement. and Loiseau's simplicial complexes that he had constructed. So now when we're trying to figure out whether the chromatic number of the Nasr graph is k plus 2, let us see if there is a very natural way to get a good upper bound. So now let us take x1 to be the collection of all, let's partition the set of vertices. So this is a set of all vertices in kg and k, such that 1 belongs to V. So let's go iteratively now. So this is a set of all vertices such that 1 does not belong to V, but 2 belongs to V. Continuing this way, xi is a set of all V in the vertex set, such that 1, I minus 1 do not belong to V, but I belongs to V. So I continue till x n plus k plus 1, which is the set of all vertices such that 1 to n plus k do not belong to V, but n plus k plus 1 certainly belongs to V. The reason I've come here is it's very easy to notice at this stage that xi must be empty for all I greater than n plus k plus 1. Right? Okay. Now some very simple observations. If you take the elements w1 and w2 in xi for some I, from 1 to n plus k plus 1, what we notice is that I belongs to both W1 and W2, which implies W1 is not adjacent to W2, essentially telling you that any two elements in the same set, we have partitioned the vertices. So any two elements in the same partition will not be connected by an edge. So which essentially means at this stage that you can assign one color to each of the elements in each of these sets. So this is probably going to come and tell us that we might expect the chromatic number of the Nasr graph to be n plus k plus 1. So the crucial question at this stage is, do we need this many colors or can we do with less? Okay, so now let us look at xk plus 2. Xk plus 2 will be the set of all, I'll just get the definition here, vertices, such that 1 to k plus 1 does not belong to V, but k plus 2 belongs to V. Now notice that any vertex here will be a subset of the set from k plus 2 to 2n plus k, which is a set of cardinality 2n minus 1. Now any element, any of the vertices will have to have cardinality n, which essentially tells us this, that if we take any two elements belonging to the collection xk plus 2 union xn plus k plus 1, both these, because with the counting argument what we can see is W intersection V can never be empty, which implies that V and W will be never adjacent to each other. So all elements in the collection xk plus 2 union xk plus 3 union so on till xn plus k plus 1 can all be given the same color, which essentially now tells us that the chromatic number of the Nasr graph has to be less than or equal to k plus 2. So from n plus k plus 1, we have brought it down to k plus 2. And so an upper bound is available rather easily. But is this, the Nasr conjecture now says that this is not only an upper bound, it's actually a tight upper bound. So it's exactly this quantity. So in 1978, Loiseau gave a proof for the Nasr conjecture or for showing that chromatic number of kg and k is equal to k plus 2. And he introduced a simplicial complex, especially for this particular graph. So the essential idea over here was to start with a graph G, try to assign a nice topological space to the graph. Suppose you call this xg. So this is actually a finite regular cell complex, and the cells are essentially products of simplices. Then you look at the topological properties of xg, and then try to pull out some interesting combinatorial properties of G in order to study this particular problem. So I'll give you an idea of the kind of simplicial complex that he used here for this proof. So he introduced what is called the neighborhood complex, right? So let us start with a graph. So the neighborhood complex Ng of G, this is a simplicial complex such that the zero simplices of Ng are the vertices of G. And a subset of the vertex set forms a simplex in Ng if and only if all the vertices of A have a common neighbor. Okay, I'll just illustrate this with an example. So let us take the complete graph on 4 vertices. When you're trying to construct a simplicial complex, it's sufficient for you to determine all the top dimensional simplices and then take all the subsets to form your simplicial complex. Now notice this. 1, 2, 3, each of these vertices 1, 2, and 3 is connected to the neighbor 4. So that means 1, 2, 3 will form a 2-dimensional simplex. Similarly, 1, 2, 4 will also form a 2-dimensional simplex. 1, 3, 4 and 2, 3, 4. Now the neighborhood complex, so this I call the neighborhood complex of K4. Now when you try to visualize this, what you can see is a neighborhood of K4 actually is going to triangulate the 2 sphere. This is going to have the same homotopy type as the 2 sphere, which is S2. So this brings me to probably the only topological concept I will really talk about today. So N-connectedness, since I'm using 2 spheres and same homotopy type and all that, I'll just use this, give you this definition for N-connectedness. So a topological space X is said to be R-connected if every continuous map phi from Sn to X, Sr to X can be extended to a continuous map phi tilde from the closed disk dr plus 1 to X, where -1 is less than or equal to R, less than or equal to, this is N. In other words, what you're actually saying over here is pi I of X is equal to 0 for all I less than or equal to R. That is pi 0, pi 1, pi 2, etc. All these are going to be 0 for, I strictly less than R. Okay. So now we are in a position to state what Lovász said in 1978. Let G be a graph and K be an integer such that K is greater than or equal to 1. Then neighborhood complex of G is K connected, implies chromatic number of G is greater than or equal to K plus 3. So Lovász proved this result, and using this he proved the Naser conjecture. This actually opened out this whole area of topological combinatorics in a sense, and a lot of very nice proofs for this particular Naser conjecture have come in after that. One of the most nice proofs to see uses the Boursa-Coulomb theorem. But I will give an alternate formulation of how Lewis actually proposed his conjecture. I'll introduce you to one more complex called the home complex. So let us start. So I'm going to define the home complex because I just want to give you an idea about what kind of work has happened here. So the home complex for some two graphs G and H, so I'll call this home GH. So this is a subcomplex of this broad simplicial complex phi on vertex set of H, where X runs over the vertex set of G, such that any cell sigma element of pi sigma X, which you're indexing over the vertices of G, is an element of the home complex if and only if XY element of vertex set of G and X adjacent to Y implies sigma X comma sigma Y is a complete bipartite subgraph of H. So these are just products of simplices, that is, each cell is just a product of cardinality of VG simplices of dimension sigma X minus 1. So geometrically, what is actually happening here is if you start with a cell in home GH, it can be indexed with a set map from vertex set of G to the power set from which you remove the empty set, such that X comma Y belonging to the H set of G implies for all X tilde element of phi X and Y tilde element of phi Y, X tilde Y tilde belongs to H set of H. So if you try to use this definition, you can see very easily that home of this graph is going to be, so these are my vertices here. Okay, let me just use a different color. So one can spend some time and actually get a number of other nice properties here, but I will not get into that. And what is also easy to notice here is home. This is going to be covariant in the second coordinate. It's a covariant functor from the category of graphs to the category of topological spaces. And in the first coordinate, it is going to be contravariant. So now that I've defined the home complexes, I can state what the conjecture Lewis had made after this, where he said that home K2G, which is nothing but the neighborhood complex, is K connected, implies chromatic number of G, he gave another lower bound here, is greater than or equal to K plus 3. So this can also be restated as follows. That is, he also gave this homes, the cycle graphs home C 2R plus 1, comma G is K connected, implies chromatic number of G is greater than or equal to K plus 4. He gave a better bound here. So in these cases, R and K are integers, where R is greater than or equal to 1, K is greater than or equal to minus 1. So this was proved by Babson and Kozlov in 2003. And they also showed that home improved on this earlier result. Home Kn comma G is K connected, implies chromatic number of G is greater than or equal to K plus M plus 1. And they, using Quillen's theory, they were able to show that home Kn, Km, Kn, this is going to be of the same homotopy type or homotopy equivalent to a wet sum of n minus m dimensional spheres. So this started the study of a lot of topological properties of the home complex. So with my student, we had studied certain exponential graphs, and for which we computed the homology groups using Z2 coefficients. So home K2 cross Kn, comma Kn plus 1 with Z2 coefficients, we had shown was Z2. If k is equal to 0 and n minus 1, Z2 k p minus n factorial plus 1 if k is equal to 2, and 0 otherwise. And we had also studied the connectedness of the general graphs, home K2 cross n, comma Kn, and this we had shown to be m minus n minus 1 for m greater than or equal to 4 and m minus 3 otherwise. In this case, we tried to study nice acyclic matchings, and we used that to compute the to get a Morse complex. We use discrete Morse theory here to compute this proof. So I have in this talk I have talked about a very specific simplicial complex associated with a graph. That simplicial complex being the neighborhood complex. So Arvind was trying to look at the independence complex, and the independence complex is the complex which is where the simplices are going to be independent sets. And there is this interesting result which was proved in 2007, which said that the independence complex would be shifted. Given a particular graph, Ig would be the independence complex. So the independence complex is a shifted complex if and only if G is a threshold graph. So this was rather interesting, and there were various other properties that the authors in this paper had studied about threshold graphs, and they had also studied neighborhood complexes and higher independence complexes here. So it is known that for a caudal graph, for example, the independence complex is vertex decomposable. So what we were trying to do was look at a very specific class of caudal graphs, namely the two trees. And for the two trees which were not weakly quasi-threshold graphs, we're just trying to determine whether there was some kind of, whether we could come up with a connection between the homotopy type and some graph theoretical properties that we were looking at. Hopefully it'll come out in due course. So this is a very rich and vibrant field wherein, especially with persistent homology and all that, there is a lot of application which is happening. Lot of work for topologists and graph theorists and lots of people. So I think I've also overshot my time. I'll stop at this point, and if there are any questions anybody in the audience would like to ask, I'll be happy to answer. I would again like to thank the organizers for giving me this opportunity to talk in the memory of Arvind, and thank you very much.
Thank you. Nice talk. Yeah, I just want to ask this Borzabulon proof. That is the one I have looked into. I mean, any connection with the Loash proof, or is it completely a different type of idea?
Sorry, can you just say that again?
The proof which was given later on using the Borzabulon theorem.
Yes.
For the Kneser conjecture. Does it have any connection with the Loash proof at all, or it's a completely independent?
Oh, the variety of proofs. One of the proofs which, but more or less everything uses the basic idea of the Borzabulon theorem. The idea remains constant, but the way the proof has evolved over the years has changed a lot. But essentially, even Loash started with the idea of the Borzabulon theorem.
Oh, okay. Any question, other question or comment? Okay.
Thank you very much. Thank you very much, Dr. Bapat. Yeah, thank you.
We are over to Raksha or Prasad.
Thank you.
Yeah, Sukanta, it is your turn. You are the organizer.
No, we have a break now till
Yeah.
3:15.
Right. Raksha, you can announce the break then.
Yes, sir. Thank you very much. Thank you, professors, for attending this session. We now have a short break. Next session will start at 15:15 IST. Thank you.
Raja, how are you?
Yeah, I am fine. Yeah, things are going on. Omicron is coming now. So.
Is it making too much of noise at your place?
Not that, but conference planned for January, so I think I am worried.
Yeah, that is understandable. Yeah, I was feeling comfortable. All of a sudden, a week or 10 days before this Omicron entered.
So, how many are there physically now?
Only local people.
Only local.
One from outside, from Florida, was here. Otherwise, nobody else from outside are here.
Yeah.
Only local students, participants, faculty are gathering together.
Yeah, we had actually.
Next week, we from next Monday onwards, we have 15 days long workshop led by Raghavan. Raghavan will be here, and Bapat will also come towards the in the second week. And some few students are there from outside and local students, and some are attending through online.
Yeah, I hope things don't become worse.
Yeah, definitely. I hope for the best, and gradually this will slow down, and I don't know whether I should say that it will vanish. It may not vanish, but we'll learn how to live with that.
Yeah.
Had your coffee?
Yeah, just now.
I'll have a coffee in 5 minutes and come back.
Yeah. Okay.
Thank you.
Shall we start now?
Yes. Welcome back. Am I audible, sir?
Yes, yes.
So, welcome back to the next session. This technical talk session is dedicated to Professor Lal from his students. So, in this session, we have with us Professor Satyanarayan Reddy Arikatla, Shivnadar University, Uttar Pradesh, India. He will be talking about exponents of primitive symmetric companion matrices. We have Kamal Lochan Patra from National Institute of Science, Education and Research, Bhubaneswar, India. He will be delivering talk on characteristic center of a connected graph. Also, we have Professor Sumit Mohanty from Gandhi Institute of Technology and Management, Visakhapatnam, India. He will be delivering talk on trees with matrix weights, Laplacian matrix, and characteristic like vertices. And last speaker is Professor Tony Thomas from Kerala University of Digital Sciences, Innovation and Technology. He will be talking about graph centrality measures and mobile malware detection. I now request Professor Rajaram Bhatt from ISI Bangalore to chair the session. Over to you, sir.
Thank you. Thank you. It's an honor. So actually, we are already short of time. It's a very tight schedule. Hardly any gap. So 20 minutes, and so each speaker 20 minutes and 4 speakers, and with no gap. So and we are 5 minutes late. So I think it's better to start immediately. So first speaker is Satyanarayana Reddy Arikatla. So please. The title has already been announced. So.
Good morning to all of you. I am thankful to the organizers for giving this opportunity. I completed my PhD under the supervision of Professor Arvind Kumar Lal and Professor Shashank K. Mehta from Computer Science Department of IIT Kanpur. Professor Arvind Kumar Lal sir used to call me as Satya. My full name is Satyanarayan Reddy. Professor Arvind Kumar Lal is very helpful throughout my PhD period. He gave me complete freedom for the research. But however, whenever I am in a difficulty, he helped me to come out of that situation. Still, I remember in my first work, the way of my writing is very bad. He explained me in each and every line. He used to ask me to sit beside him, and in the computer, he used to explain me how to write each and every step. By the way, he wrote even half of the paper also, half of the article. Asked me to complete the remaining article in the similar lines. Even after completion of my PhD, I involved in a course by E-Pathashala under UGC, and Professor Lal sir gone through all the 38 modules which I prepared and gave critical comments at each and every point. There are many events of this nature. He helps everyone, but he will not expect anything in return. That is one of the reasons that he is always happy person, a jolly person. He even not informed me joining of his son in our university. I came to know later. He is not interested to take favor of any person. That's what I want to convey. Many great memories with him, but time is not sufficient to discuss. But I'll discuss these things at some later occasion. I hope it will come. Now I will start share my work which I done with Professor Arvind Kumar Lal. Then later I will tell about my contributed talk today. Yeah, so the topic is exponents of primitive symmetric companion matrices. The outline of the talk is like this. My collaboration with Professor ICLAA first. Then I will tell about the contributed work. Then some references. So first, the collaboration work with Professor ICLAA. So let F be a field of characteristic 0. Mn of F denote the set of all n-by-n matrices with entries from the field F. It is known that Mn of F is an algebra over F, right? Here algebra we mean both vector space as well as a ring structure with some extra condition. So n by n matrix, then Fa denotes set of all n matrices which are polynomials in A with the coefficients from the field F. Then Fa is a subalgebra of Mn of F over F. And it is easy to see that Fa of X is isomorphic to the polynomial algebra quotienting with the P of X, or P of X the minimal polynomial. Because of that, the dimension of this vector space is going to be the degree of the minimal polynomial of A, right? So, and if B is any matrix in this, then B is a polynomial in A, then there is a unique polynomial that is called representer polynomial, such that B is equal to gamma B of A. Right. So gamma, if lambda is the eigenvalue of A, we know that gamma B of lambda is the eigenvalue of B. Right. So one of the main known result is that if Q of X is any polynomial which divides PA of X, the minimal polynomial of A, then this FA by ideal generated by QA, the matrix of QA, is isomorphic to Fx by Qx. This comes from the homomorphism theorem of rings. So in particular, if Qx is irreducible, then Q of alpha equal to 0 for some alpha, then Fa of X by Fa by the ideal generated by QA become a field. Okay, and then we defined that A comma QA represents the field F of alpha. That means the matrix A represents F of alpha if alpha is an eigenvalue of A. This is the way we define representation. Then we worked our first problem, we worked on that. Then later we worked on another problem that needs this definition. We all know Hadamard product of two matrices. It is a component-wise multiplication, and two matrices are said to be disjoint. Their Hadamard product is a zero matrix. Let S be any non-empty subset of Mn of C, then S is said to be closed under conjugate transformation if conjugate of A also is there whenever A is there. And it is said to be closed on Hadamard product if Hadamard product is also there of two matrices. And we denote the matrices 10 to 0 or 1 as 0, 1 matrices. One of the main result in this direction is Higman and the book on distance regular graphs written by Brouwer, Cohen and Newman. So it says that a vector subspace of Mn of F is closed on Hadamard multiplication if and only if it has a mutually disjoint 0, 1 matrix as basis. Okay, so this is very useful result while characterizing that certain things. So for that I need this definition, coherent algebra. And coherent algebra is subalgebra of Mn of C which contains I and J and closed under conjugate transformation and Hadamard product. What is J here? Matrix with all entries being 1. Okay, so coherent algebra means it contains I, contains J, closed under conjugate transformation and Hadamard product. It is called a coherent algebra. So it is easy to see that Mn of C is the largest coherent algebra. And if you J, the matrix with all entries 1, it's easy to see that its minimal polynomial is x into x minus n. So its dimension is 2. And C of J is set of all polynomials in J with coefficients from C, right? Since the minimal polynomial degree is 2, its dimension is 2. And it contains I and J. And also it contains I comma J minus I. They are mutually disjoint 0, 1 matrices. So because of the previous result, Cj is a coherent algebra. And every coherent algebra we know contains I and J. So Cj is the smallest coherent algebra. So any other coherent algebra is lies in between these two. One more thing you can observe here is that Cj is same as Cj of J minus I. J minus I is exactly the adjacency matrix of the complete graph. So we denote A of Kn as adjacency algebra. In particular A of X. X is a graph, then A of X is adjacency algebra of X by NL-Biggs notations. Okay, this so actually this C of J is A of Kn now, adjacency algebra of the complete graph. For example, if P is a permutation matrix, you take all matrices to commute with it, then it gives a coherent algebra. In particular, this is we are going to use frequently. If Wn is the companion matrix of x power n minus 1, right? I'll define companion matrix in a while, but otherwise you can think of it is a circular matrix. Means you know the first row, second row is a circular shift. So Wn is like this, and we know that x power n minus 1 is equal to its minimal polynomial is x power n minus 1, nth roots of unity are the eigenvalues, and it is equal to the product of cyclotomic polynomials, right? And in one more nice thing to see here is that this Wn square and so on, they form a basis and they are 0, 1 disjoint 0, 1 matrices. Their sum is going to be the whole J. So it is nice matrix with respect to many cases. First, it is non-negative, and second point is that for any ij, there is a k such that w power k, if I wn power k, if I do, ij center become positive. That means it is irreducible matrix, but it never be primitive. If matrix, non-negative matrix is said to be primitive, there is a unique case such that a power k, every entry become positive, matrix become positive matrix. This is an example of irreducible matrix, but not a primitive matrix. Okay. Wn actually, another way to look at Wn is the efficiency matrix of the directed cycle. Let D be the divisor of n, then zeta d is the primitive dth root. Then it is easy to see that Q of Wn is by PD of Wn is actually equal to the cyclotomic dth cyclotomic field. That means these Wn represent the cyclotomic fields. Okay, this is the one of the things which I am telling beforehand. Now, by using Wn, we are computed the there is a representation for cyclotomic fields and their subfields also. And A is a matrix is circulant if say circle shift of the first row. It is sufficient to know the first row. Other rows are coming from that. One of the interesting result given by in the book of Davis on circulant matrices is that a matrix is circulant if and only if it is a polynomial in Wn, because all its eigenvalues are distinct. That is in fact true for any matrix. All eigenvalues are distinct, a matrix is commutes with it if and only if it is a polynomial. Now C of Wn is set of all circular matrices, is a coherent algebra of dimension n. Okay, and lastly, the component matrix of a polynomial is defined like this. We all know. So it is first n-1 rows are fixed. So here, and it is actually circular shift. The last row is the coefficients of this polynomial, right? And the C0 is the constant term up to Cn-1. So C of f is a 0, 1 matrix if Ci belong to 0, 1. For example, Wn is equal to component matrix of x power n-1. So what are the problems we worked in collaboration with Aringal are these things. The problem of finding smallest order circulant matrix representations for cyclotomic fields and their subfields. The problem of finding smallest 0, 1 component matrix having zeta n is an eigenvalue. And another problem is that finding necessary and sufficient conditions for circulant graphs to be singular or non-singular. The problem of finding necessary and sufficient condition for a graph such that its adjacency algebra is a coherent algebra. Right? So these problems we worked and they are published here. For example, the first representation of cyclotomic fields and subfields are published in Indian Journal of Pure and Applied Mathematics. And there is circulant graphs, non-singular circulant graphs and diagrams. It is published in Electronic Journal of Linear Algebra in 2013. And this pattern polynomial graphs, we called those graphs in which adjacency algebra becomes a coherent algebra. We call those graphs as pattern polynomial graphs. That Lal sir himself presented in India Taiwan conference of discrete mathematics in 2013. So all these are in 2013. And this paper is also uploaded in archive and also submitted to a journal now. It is under review. Now I'm going to the present contributor talk. It is a joint work with Dr. Murlima Lanej. Now she is assistant professor in Admas University, Calcutta. So here a symmetric matrix, a symmetric component matrix. A is a component matrix and A plus A transpose is the just we are adding and we are calling that as a symmetric component matrix. What we do, first we take A as a 0, 1 component matrix and we'll take A plus A transpose. Then it is a non-negative matrix, right? And in this work we found total number of primitive and imprimitive symmetric component matrices. See, it is easy to see that first n-1 rows are known, only the last row. And the last row also for A is a component matrix with the 0, 1 entry. So last row also only zeros are 1. So total there are 2 power n matrices are there. Then we are taking A plus A transpose. There we are checking how many are primitive, how many are imprimitive. This is the counting problem as well as Whenever they are primitive, we are counting the exponents. We found formulas to compute the exponents of every primitive symmetric component matrix. And exponent set is completely characterized for these cases. We also obtained a number of primitive symmetric component matrices with a given exponent for certain cases. We are not able to do for all cases. Now we'll explain this. Let X be a non-empty subset of M and of R, some matrices. Then exponent of X is a natural number such that there is a primitive matrix A in X such that exponent of A equal to K. So sometimes the way we choose X, they're not at all primitive matrices. Means primitive matrix first non-negative, and there is a case as a power K equal to positive matrix, right? And the smallest k is called exponent of A. So if that none of those matrices are available in X, then it is empty set. E of X is empty set. We know that positive matrices are exponent 1. So 1 belongs to Mn of R. Directly if my X equal to Mn of R, then 1 is there. So one of the famous result is that Wieland proved that he given an upper bound for the exponent, that is n minus 1 whole square plus 1. This bound is also called Wieland bound. And with this remarkable result that E Mn of R is contained in 1 comma omega n. Omega n is upper bound. But later in 1964, Dumage and Mendelssohn showed that it is a proper subset. There are some gaps. Okay, this is overall Mn of R. But here we are now confined to a particular case. So this is the graph related to Wieland, and you can easily see that 1 map to 2 map to 3 and so on. N minus 1 map to 1, that is this graph, and it has the largest exponent. That means you take the extensive matrix of this as primitive, and the exponent is omega n. Now we'll come to the problem. So we took the component matrices, right? This A's are belong to 0, 1. Since first n minus 1 rows of every matrix in Cn is fixed, it is sufficient to specify the last row. Thus, there is a bijective connection between Cn and Bn, where Bn is the set of all binary strings of length n. In particular, the Cn is equal to cardinality of Cn Bn equal to 2 power n, right? And later what we done, we took a matrix A from the Cn and we added A plus A transpose. That is we call a symmetric component matrix. Then we collected all of them. Cn of alpha beta is a notation for that. Finding given matrix primitive or non-primitive very much depends upon alpha and beta values, right? Okay, now so for example, if n equal to 3, my beta 3 equal to binary strings, 8 strings are there. So we have 8 component matrices will be there, right? This first matrix is corresponding to x cube, and one is x cube minus x square and so on. The last one is x cube minus x square minus x minus 1. Okay, since these matrices, this is obtained, this matrix is obtained from this by A plus A transpose. So these two matrices are imprimitive, means you do any power, it never become positive. Because of that, the PS3 of 0, 0 is empty set. Whereas other matrices, PS3 of 0, 1, beta value 1, or even alpha 1 also, then they are primitive and their exponents also given, right? So first two matrices exponent is 4, exponent set is 4, means both have exponent 4, and the remaining cases it is 2 only. That you can easily check. If you square them, these last 4 matrices, you can easily check it is a positive matrix. So the work in this, our work in this particular area is that finding the all primitive and imprimitive matrices. It is a combinatorial problem. How many are there? That is a one problem, right? And then exponent sets of all these. What are the possible exponents in all these cases, right? And that also will count by these alpha beta values, right? That is the way we divided the work. And also this another interesting thing is, once we know the exponent, how many matrices are there with that exponent? That is denoted as Nn of alpha beta, right? So this particular thing we unable to count for all the cases, but we counted for certain cases. Okay. So before this, actually, we worked only for the non-symmetric, just component matrices we took, and that work we published. That work is published in Rocky Mountain Journal. And then while doing that work as well as this work, you see that last row is important. So that in that last row also how zeros are there. So the zeros are consecutive zeros playing a role. That's why first we counted number of binary strings of length n with x zeros and longest k runs of zeros. Okay, so now the work which we done in this paper are, so we counted the number of primitive matrices. So beta equal to 1, alpha can be 0 or 1, then we counted the total equal to 2 power n minus 2, that is easy. Then 0, 0, both alpha, beta is 0, then the number and like that. So with this what happened, we counted all the primitive as well as automatically 2 power n minus this number is in primitive matrices. So this is about this theorem. And before going further, we need some terminology. So to make it more understandable, so first to look at here, this u equal to 2, 3, 5, 7 and all. Then here, so I took 2, 3, these are consecutive, 5 is single, then 7, 8, 9, 10 consecutive and 13, 14. So if you take any set u like this and we took divided into u1, u2, ur, and we take the maximum value of that is m of u, right? And what are v1, v2? So I'll explain first with a graph. So look at this graph. So here vertex set is v comma 10. V comma 10 means that vertices are counting from 1 to up to 10. Okay, now the last row correspond to the vertices which are adjacent to 10. So there is an edge from 10 to 1 and 3, 5, 7 and 9, but there are no edges from 10 to 2, 4, 6 and 8. So that is my V1. V1 is no edges from, they are not adjacent to 10 and V2 is adjacent to 10. Okay. So with that we define V1, V2 and then V1 we are done this. M of V1 is important. M of V1 is the, so we divided V1 into partitions and the longest consecutive one, that is M of V1. Right? In this particular case, all are independent, so M of V1 equal to 1 itself.
Can you wind up now?
You can easily check that this matrix is going to be imprimitive. It is not primitive.
I have made sure that total time
now,
is managed.
the first result in this direction is that if both alpha, beta are 1, right? That means the first value as well as last value in the last row are 1. Then exponent set is very easy because see, last one beta value 1 means there is a self loop. Then they are easy actually to count and the exponents also less, very smaller exponents we get there. So in this case, exponent of A, of course, it depends upon T value, that T again depend upon M of V1. So these are the exponent of A and all.
Total time is managed within. So it's all right. We can proceed, I think.
So we counted that number of primitive matrices with given exponent also. That is the n of 1, 1. Okay, and also PCN of 0, 1. Okay, and here minimum of V2 is required. So depending upon that, we counted exponent of A and also number of primitive matrices, the given exponent also we counted in this. But sorry for some notations Fn minus 3 and these are available in this second paper. Okay, yeah. And similarly, we computed exponent set of, so as a corollary to the previous result, exponent set of Pn11 is completely characterized. That is 2 into t plus 1 and also exponent set of Pcn01 also. Okay, now coming to beta equal to 0 case. Okay, now these are little complicated, but we given a complete exponent set here. And also not only that, here for given A, what is the exponent of A? That depends upon certain values. So there are some more notations. So I'm sorry for not giving those. At the end, I will share you the file where we can see these things. Link. Okay, so but what is the theorem is telling about is that what given A in PC in 10, what is the exponent of A? That we computed here. And here difficult to compute all the number of mats with given exponent, but we computed one maximum value, maximum exponent. That is about that result. And finally, we also computed exponent set of PCN of 0, 0. And many other results are there, but now we are not stating. For more results and details, please visit this archive website. And if there are any other queries also, you can write to me. And once again, many thanks for your patience. And yeah.
Okay, thank you. So, any questions or comments? Any questions? No? Okay, thank you. Then maybe we move to the next speaker. Professor Kamal Lochan Patra from NICER is talking about characteristic center of a connected graph. Professor Patra. Professor Kamal Lochan Patra.
Let me thank the organizer for giving me this opportunity to say something for this session, which is honored for Professor Lal. I'll start the title of my talk is Characteristic Center of a Connected Graph. Whatever I will present is joint work with one of my PhD student, Dinesh Pandey. So, as the title suggests, it has something to do with the centrality of connected graphs. So, people have started centrality of connected graph, particularly for trees, and there are many centers defined for it. And all these central part, particularly connected for connected graphs, are defined combinatorially. We will define characteristic center of a connected graph through algebraically. So, for this, let G be a graph with vertex set V, which is equal to V1 to Vn, and edge set E. The Laplacian matrix of G defined as Lg equal to Dg minus Ag, where Ag and Dg are adjacency and diagonal matrices of G respectively. One can easily check from the definition that Lg is symmetric, and it is easier to prove that it is positive semi-definite also. So all its eigenvalues are non-negative and real. At Sg, which is equal to lambda 1, G, lambda 2, G, lambda n, G is the Laplacian spectrum where 0 less than equal to lambda 1 G, lambda 2 G less than equal to lambda 2 G up to lambda n G as the eigenvalues of Lg. One can check from the definition that the row sum of Lg for any graph equals to 0. So 0 is an eigenvalue with all one vector is an eigenvector. So this is an eigenpair for Lg. Fiedler in 1973 first noticed that lambda 2G, the second smallest eigenvalue, is greater than 0 if and only if G is connected. So, knowing lambda 2G, which measure the connectivity of graph, he called lambda 2 or second smallest eigenvalue of G is the algebraic connectivity of G. We denote it by mu G. So he proved some remarkable result associated with lambda 2G or mu G and the corresponding eigenvector. So an eigenvector corresponding to mu G, we call it as a Fiedler vector of G. let y be a Fiedler vector.
Yeah, your
By
display is not
yv,
showing.
we mean the coordinate of y corresponding to the vertex v. So let y be a Fiedler vector for a connected graph G. Then because it is positive, definite, or symmetric, so y is perpendicular to E. So the entries of y must contain some positive and negative part. So based on this, we will define something called characteristic vertices of G. A vertex V is called a characteristic vertex of G with respect to y if it satisfies one of the following two conditions. First, one of the following two means first, either yv equals to 0 and there exists a vertex u adjacent to v so that yu not equals to 0, or there exists a vertex u adjacent to v so that yv into yu strictly less than 0. That means both are, if it is 0, there is a non-zero vertex associated with it or adjacent to it. If it is non-zero, then there is a vertex which sign opposite to v, so less than 0. So based on that, we define something called characteristic set of G with respect to y, the set of all such characteristic vertices. So we denote it by chi G1. Fiedler actually first proved that let y be a Fiedler vector for a tree T, then chi Ty is either a single vertex or two adjacent vertices. Furthermore, chi Ty is fixed for any Fiedler vector y. But he proved that the characteristic set for a tree consists of either a single vertex or two adjacent vertices, and it is fixed for any Fiedler vector y. For a characteristic vertex V, if the condition 2 holds, then U is also a characteristic vertex of G with respect to y, which can be seen from the definition what we gave. In this case, the edge UV is known as the characteristic edge of G corresponding to y. The term characteristic edge is first given by, the name characteristic edge is first given by Professor Baport and Poti. They have studied the cardinality of characteristic set in terms of characteristic vertex and edges for a connected graph. So for we are considering characteristic vertices only. So characteristic edges are basically two adjacent characteristic vertices. For a vertex V, a connected graph G, for a vertex of a connected graph G, let C1, C2, Ck be the connected component of G minus V. Note that K greater than equal to 2 if and only V is a cut vertex of G. For I equals to 1 to K, let L hat Ci be the principal submatrix of Lg corresponding to the vertices of Ci. Using Perron-Frobenius theory, one can prove that the Li, we are taking a connected graph G. So L hat Ci is invertible and L hat Ci inverse is a positive matrix, which is called the bottleneck matrix of C. Say L hat Ci is a positive matrix can be followed from the property of it is also an M matrix. So we call L hat Ci inverse a bottleneck matrix of C. By Perron-Frobenius theorem, L hat Ci inverse is a simple dominant eigenvalue called Perron value of Ci at V. The component Cj is called a Perron component at V if its Perron value is maximum along the component C1 to Ck at V. So this Perron component, Perron value, bottleneck matrix, this idea used by Kirkland, Follott and co. to study the eigenvalues, basically Fiedler vector and algebraic connectivity. So they proved the following result for trees. Let T be a tree on n vertices, then the edge Ij is the characteristic edge of T if and only if the component Ti at vertex J containing the vertex I is the unique Perron component at J, while the component Tj at vertex I containing the vertex J is the unique Perron component at I. If it is for a characteristic vertex, let T be a tree on on n vertices, then the vertex V is the characteristic vertex of T if and only if there is two or more Perron components of T at V. Also, they proved that let T be a tree, and suppose that V is not a characteristic vertex of T, then the unique Perron component V contains the characteristic set of T. So using these three, one can see that for any Fiedler vector Y, for path Pn, where the vertices are numbered 1 to up to n, chi pny, the characteristic set of pn with respect to y is n by 2 and n by 2 plus 1 if n is even, and n plus 1 by 2 number if n is odd. For any Fiedler vector y of a star graph is equal to the vertex which is degree n minus 1 in k n 1 minus 1. It is clear that the characteristic set of a tree is independent choice of Fiedler vector. But this is not true for a general graph. We have the following example. If you take a cycle on 4 vertices, the multiplicity of algebraic connectivity is 2. We have 2 linearly independent eigenvectors like this, so y1 and y2. And if you take chi with respect to c1, which is equal to v2, sorry, y1, which is equal to v2 and v4. For y2, it is v1 and v3. So this is different. So to define as a central part of a connected graph, independent of the Fiedler vector, we define characteristic center as the following. Let G be a connected graph and LG be the Laplacian matrix of G. Then the characteristic center chi G of G is given by chi G equals to V belongs to Vg, where V belongs to chi Gy for some Fiedler vector y. So the way we have defined it is independent of the Fiedler vector. So the term characteristic center is actually first used by Zimmermann for trees in 1998. So we have extended this to general graph. Clearly for a tree, it is independent of Fiedler vector, and chi t equals to chi ty for any Fiedler vector, and chi pn, whatever we have discussed earlier, is this, and chi for star graph is equal to the center of the star graph. Here I am taking n greater than equal to 3. Also, the characteristic center of a tree consists of either one vertex or 2 adjacent vertices. Because it is independent for a tree, it is independent of Fiedler vector. This result is also true. So while studying the central part of a connected graph, so these results are also true for the way the central parts of connected graphs are defined, and also in most of the case when it is defined for connected graph, the central part always lies in a block. So what will happen to characteristic center? So let y be a Fiedler vector of G. We call a vertex V has a positive valuation, negative valuation, or 0 valuation depending upon whether yv is positive, negative, or 0 respectively. So Fiedler in 1975 proved the following. Let G be a connected graph and y be a Fiedler vector of G. Then exactly one of the following 2 cases hold. There is a single vertex. There is a single block B0 in G which contains vertices with both positive, negative valuation. Each other block contains either only positively evaluated vertices, only negatively evaluated vertices, or only 0 evaluated vertices. Every path P starting from B0, which contains at most 2 cut vertices in each block, and exactly one vertex K in B0 has the property that the valuation of the cut vertices of G lying in P from either an increasing or a decreasing or a 0 sequence along this path accordingly to whether yk greater than 0, yk less than 0, or yk equals to 0. In the last case, all the vertices on P have valuation 0. The graph I have shown for while defining the characteristic vertex, one can easily check that. So the other case is no block of G contains both positively and negatively evaluated vertices. There exists a unique vertex Z of valuation 0, which is adjacent to a vertex which is non-zero valuation. The vertex Z is a cut vertex, and each block contains either the vertices with positive valuation, vertices with negative valuation, or vertices with 0 valuation. Every path starting from P, which contains at most 2 cut vertices in each block, has the property that it behaves like the earlier ones, but there are only two such cases. So based on this and using the Perron component and Perron value and idea, Kirkland and Follett proved the following. Let G be a connected graph, then either case 1 holds for every Fiedler vector, or such and each such Fiedler vector identifies the same block H being the one with positive value or negative value to vertices, or case B holds for every field vector, and each such vector identify as the same vertex of Z, which is valuation 0 valuation and is adjacent to one of the non-zero values. So based on this, we can, the way we have defined characteristic center, we can say that the characteristic center of a connected graph G is contained in a block of G. So this, the characteristic center, the behavior of the characteristic center, what we defined is behavior like a central part. So we proved the next result based on whatever the property also proved from other central. We call the subgraph induced by chi-G the characteristic subgraph of G. So what we proved, for any graph G may be disconnected, there exists a graph GCH such that the characteristic subgraph of GCH is isomorphic to G. To give the proof, we have to first construct GCH. Given a graph G with vertex set V1 to Vn, you take 4 new vertices U1, U2, U3, U4, all the vertices of G adjacent to U2 as well as U3, and U1 is adjacent to U2 and U3 adjacent to U4. We are giving the order for Laplacian matrix is U1, U2, then V1 to Vn, then U3, U4. Take lambda equals to n plus the n plus 2 minus square root of n square plus 4 by 2 as n greater than equal to 1. So lambda lies between 0 and 1, or lambda it belongs to in the open interval 0, 1. It can be checked that lambda is an eigenvalue of LGCH with the corresponding eigenvector this. What we proved next, that the third smallest eigenvalue of 0 is this is a connected graph. So 0 is the smallest eigenvalue. What we proved, the third smallest eigenvalue is greater than equal to 1 using some matrix theory result, which is basically Courant-Willy theorem, and to prove that the third smallest eigenvalue, basically they prove based on the interlacing of eigenvalues of principal submatrices. So the third smallest eigenvalue is greater than equal to 1. So this is the algebraic connectivity, and its multiplicity is 1. So the eigenvectors corresponding to lambda is the scalar multiple of this. One can see that V1 to Vn are the characteristic vertices of LGCH for any graph G you take. So this prove our result. We also proved that let G be a connected vertex transitive graph, then chi G equals to Vg, which is actually true for other central part defined in a graph. This can be proved because of vertex transitivity. So the automorphism, for every automorphism, we have a permutation matrix using that idea. One, we can prove that the chi G equals to Vg. So we ask the question, suppose you take a connected graph with chi G equals to Vg, is G vertex transitive? Actually, the answer is no, and the counterexample is not that straightforward. But consider this graph, which is a non-regular graph because this is 4 and 3. It's a non-regular distance balance graph. One can check that the eigenvalues are this. So algebraic connectivity is 3 minus root 3 of multiplicity 2. So these are two linearly independent eigenvector which covers 1, 4, 8 and 2, 4, 9. If you take y1 minus y3 is again an eigenvector which covers 3, 6, 7. So in this case, chi G equals to Vg. So it is nice. This there's a study about this graph in 2009 on 10 by Klajvar and other people. So this gives us a counterexample this way, but it will be interesting to know whether for every distance balanced graph, chi G equals to Vg. So these are some references for Fiedler. The results are put here. Kirkland and Fowler, you can find the result in this paper by Klajvar, and where they have studied on distance balanced graph. This example is there, but not in terms of characteristic center. So what the results, whatever we have proved, can be found in this paper, which is in archive. Zimmerman paper, where he first used this term characteristic center. So in this archive paper, we have also mentioned about other results. If you have any question, please let me know.
Thank you. A very interesting talk. So are there any questions? comments? No.
Raksha, please explore if there is any question from audience.
Participants, if there are any questions, please raise your hands.
Okay, I guess there are no questions.
Patra is with us. Sir, if you want to speak few words, please.
Yeah, our next speaker is Sumit Mohanty from Gandhi Institute of Technology. We're talking about trees with matrix weights.
Hello everyone. My title of the talk is Trees with Matrix Weights and Laplacian Matrix with Characteristic Live. As title suggests, we are going to present some lectures, trees with matrix weights assigned to its edges. And this is a joint work with one of my students, Shweta Ganesh. We begin with the definition of Laplacian matrix. If given a graph on n vertices, Laplacian matrix is a n cross n matrix. That means the rows and columns are associated with the vertex edge. And if the weights are denoted by WE to a edge, then we define the Laplacian matrix as follows. The entry corresponding to the vertices UV is 0 if the two vertices are not adjacent, minus of WE if E is the edge between these two vertices, and the diagonal entries are the sum of the weights corresponding to weights where the sum is over the edges which are incident to the vertex P. And it is known that it's a positive semi-definite matrix and 0 is the smallest eigenvalue, and the second smallest eigenvalue as this is denoted by mu g and is 0. It's non-zero if and only if the graph is connected. And the associated eigenvector is called Fiedler vector, is usually denoted by, if we denote associated eigenvector by y, the entry corresponding to vertex P is denoted by yv. We sometimes use L instead of Lg to represent the Laplacian matrix. This result is due to Fiedler, in which he said that if the trees are edges of the trees are associated with the positive weights, and mu t is the algebraic connectivity and y is the Fiedler vector, then we can categorize the tree into two ways. One is none of the entries of y are 0 or some of the entries are 0. If none of the entries are 0, we'll find a unique pair of vertices u and p, which those are adjacent to each other, and in Fiedler vector, the entries corresponding to u and v are opposite side. When on the second type of tree, when the sum of the entries in the Fiedler vector is 0, what is so? There exists a unique vertex x. The entry corresponding to vertex x is 0, but there are adjacent vertices which are not 0. So in this way, it divided the set of trees with positive and 2 type. Type 1, when the unique vertex are there, when type 2, when there is a unique edge attend corresponding to vertex UV part A. And if the unique vertex attend, it is called characteristic vertex. And if there is a unique edge, this property attend is called characteristic edge, which is part A. Yes. This particular characterization is further, this particular notion of characteristic vertex is further characterized by Kirkland and others in a paper in 1996, in which he showed that these things can be represented in some spectral areas, some bottleneck matrices. Let us understand that more. So, given a tree, if you delete a vertex, then the tree will be disconnected, and the connected components of this connected components are called the branch at that vertex. And if we consider the Laplacian matrix and delete the rows and columns of a of the that Laplacian matrix and consider the principal symmetries called LV, denoted by LV. It is called reduced Laplacian, and it is a block diagonal matrix, and each of the blocks is basically corresponding to a branch at, and this is an invertible matrix. The inverse is denoted by MB, and corresponding to the branch, the block diagonal entries, block diagonal blocks of MB is called the bottleneck matrix. ICLAA and others in his paper in 1996 also found the inverse of this matrix, and the inverse is quite interesting in a nature that take two vertices in the branch. The entry corresponding to those two branches are nothing but the sum of the weights in the reciprocal weight, where the sum is over the edges, which is common to from both x to b and y to b as defined here. Before proceed further, we need to define few notations. One of the notation is like this: if you take two distinct vertices, the branch at u containing v is denoted by buv, and in that case, the bottleneck matrix will write b. Bottleneck matrix will denote it mv of u instead of mv of b of u. Make it simpler notation wise. And this MB, this bottleneck matrices are matrices with positive entries, and by Perron-Frobenius theorem, it is known that the spectral radius is a simple eigenvalue. That's why the spectral radius of the this bottleneck matrix are called Perron values of B of the branch. And among all the branches, whichever the largest spectral radius, whichever the largest Perron value is called Perron branch. And that is in fact the spectral radius of full matrix, because we are dealing with block diagonal matrix. Now we are ready to state the results, alternative characterization of characteristic vertices. In this Kirkland has proved that if you consider trees with positive weights, if we have a considering a tree with a characteristic edge, the algebraic connectivity can be determined by this formula. And the third one is say that if the characteristic edge is between u and v, then bu of v is a unique Perron branch at u, and bv of u is the unique Perron branch at v. And similarly for characteristic vertex, what he found, if x is a characteristic vertex, then there are two or more Perron branch at that vertex. And the algebraic connectivity is reciprocal of spectral radius of m of x. And the third result says, if you are considering Perron branches are considering bottleneck matrices are at a vertex other than the characteristic vertex, then the branch containing the characteristic vertex is the unique Perron branch. This is the direction we want to proceed for our trees with matrices. For doing that, first we recall the definition of Laplacian matrix. In this case, suppose we are assigning S cross S matrix weights. The definition is analogously defined. The only difference is instead of the entries, we are getting block diagonal matrix, and corresponding to each vertices, the rows are row blocks and columns are column blocks. But the definition is analogous. You can see it is visible. For this type of matrix, Atik and others show that if we are considering a graph with connected graph, then the rank of this Laplacian matrix is n-1 of S, if S is the order of the weights. It is only true if the graph is a tree. And if the graph is not a tree, it may not necessarily be true. So what we observe that in case of tree, in case of tree, even if the weights are matrix weight, the behavior is somewhat similar to the trees with positives. So what we did, we tried to study this. That's why we want to study. We motivated with these results, and we found the reduced Laplacian, which is obtained by deleting the row block and column block corresponding to vertex V, and find the determinant is like this. And if it is from the expression itself, it is visible that if the weights are non-singular, it is in this reduced Laplacian is invertible, and we also found the inverse, which is exactly similar form, but it was there in the matrix positive weight. So earlier, so since in case of non-singular weight, we can define the bottleneck matrix as well, because LV is an invertible matrix. We define the bottleneck matrix exact analogous because we just proved that the inverse is defined like this. Now, once we define bottleneck matrix, now we think about whether we can define parent branches and parent value, parent branches and parent value. Answer is technically you cannot define for every case, but to define that we have to put some restriction. Where exactly you can put restriction? You can put restriction in the choice of our weights. So we choose our weight in such a way that the eigenvalues of LB, the reduced Laplacian, is positive. And that's why the eigenvalues of MV, the bottleneck matrix, is also positive. Hence, the spectral radius, in fact, is a eigenvalue. But unlike in case of trees with positive weights, in this case, the spectral radius may not be seen. But still, we call those our parent values, the spectral radius, and the branch containing maximum spectral radius is called parent branch. Now, we basically prove our result for two classes of matrix weights. One is positive definite matrix weight, and second is lower triangular matrix with positive. In case of the first choice is quite natural because the existing results are for positive weights. So extending it for positive definite is natural. And in this case also we'll find some similarity because if we assign positive definite matrix, the Laplacian is a positive semi-definite matrix, and since it is symmetric, we have many results in matrix theory which can be used, just like min-max theorem and other theorem, to find our result. But in case of lower triangular matrix, the Laplacian matrix no more a symmetric matrix. But for both the cases, we are able to prove the following: is that basically we are able to show there is a unique vertex where there are two or more parent branches, or there is a pair of vertex which is adjacent to each other. Then the parent branch of U is contained in the vertex B, parent branch of G is contained in the vertex C. So I am only in this presentation explaining the lower triangular case because this is much more combinatorial. So let us give a small outline. For that, we observe the following. If we consider two matrices, X and X tilde, where there is a block diagonal matrices, the blocks are related by this. Let us explain with the example. It will be much easier to understand what exactly this means. Suppose X is a matrix when blocks are 2 by 2 matrices. Then X tilde is defined like this. That means if you see the first entries of each of the blocks in X is the first block itself. So if you define like this, your both block matrices X and X tilde are permutation equivalent. And which theoretically also it is very simple to prove. It's a direct consequence that Kronecker product of two matrices A and B are permutation equivalent to Kronecker product of B into A. Then with this observation, what we have, whenever we consider lower triangular matrices, as X's are lower triangular matrices, the X tilde is basically lower triangular block matrix. So studying the spectrum of X is same as studying the spectrum of these diagonal entries only. Similar observation can be made for upper triangular matrix. We restrict our argument to only lower triangular. It follows exact analogy. So next, given a graph with weights, we can consider as an order plane a G and W set of weights. The G is the underlying graph, W is the set of weights. With this notation, we propose the following definition. What is that definition? Suppose we given a tree with the set of lower triangular matrices with positive diagonal entries are given as of order S cross S. Then we define trees with positive weights. And how does this define? Where the underlying graph is same, but the entries, the weights are coming from only from the diagonal entries. So given a tree, if we assign weights S cross S, we associate S trees with positive entries as follows. Given an example, let us explain with the examples. Right now, this is a tree and the weights assigned like this. Then what exactly we did? We consider a tree set W1, W2, W3. W1 you can see. We only consider the first entries of each of the diagonal entries. Similarly, for W2 second entry, W3 the third entry, and we consider trees with the positive weights as follows: T1 is with respect to W1, T2 is with respect to W2, and T3 with respect to W3. So, given a tree of tree with matrix weight of order S cross S, we can associate with S trees with positive diagonal, positive ends, positive weights. Due to this, we are able to show that our Laplacian matrix is permutation equivalent to LP tilde, which is a block diagonal, which is a lower triangular block matrix, where the diagonal blocks are nothing but Laplacian of the trees with positive. So, eigenvalues of LT is nothing but union of eigenvalues. That's why it is non-negative. And earlier we defined block diagonal bottleneck matrix. Yes, consider reduced matrix for non-singular matrices. In this case, obviously our choice of weight in such a way that it's non-singular, and the bottleneck matrix is well defined. But in this case, what extra happening? The bottleneck matrix itself can be permutation equivalent to this type of matrix, where this lower triangular block matrix in the block diagonal blocks are nothing but the bottleneck matrix of trees with positive weights Tj. In particular, if we consider 2 by 2 case, weights of order 2 by 2, the MB, which is the inverse of the reduced Laplacian, something look like this. To study the spectrum of MB, we only looked into the diagonal blocks, and diagonal blocks are the bottleneck matrix for trees with positive weights. So due to this type of observation, and proofs are a little longer, I cannot enter, but this is the main idea behind it. We associate the tree with positive weights, low triangular positive diagonality with trees with positive weights, and able to establish either we have a vertex which behave like a characteristic vertex, and we have a edge to behave like a characteristic edge. That's why those are matrices are called characteristic like vertex and or characteristic like edge. So in the process, we also able to prove that if X is not a characteristic like vertices, then the unique parent branch at X is the branch which contains the characteristic. So naturally, the next thing people will ask, what about the algebraic connectivity? In the characterization due to Kirkland and others, they prove that this characterization is also related to algebraic connectivity. What about if that in this case? We also found some similarity, not exactly the same thing. So here we need to algebraic connectivity is the first non-zero eigenvalue. Let us understand that. To proceed in that direction, we are able to show if P is a tree with characteristic edge, characteristic like edge, we are able to show this result. The proof, we can see this is similar to the result in the Kirkland's original paper, and the proof is also similar. Only we need to take care of that because we are dealing with matrices. Sometimes the results are dealing with symmetric matrices. Sometimes when the lower triangular case not symmetric matrices, we need to care for. But the idea is more or less the same as the Kirkland establish this. Once we establish this, we define a constant kappa T. Is defined like this. If E has a characteristic vertex, we define kappa T is reciprocal of 1 by rho of MB, which is the spectral radius of MB, the parent value of MB in fact. And if a characteristic edge, we define kappa T equal to this. It is easy to see whenever we consider T's with positive weights, kappa T is nothing but the algebraic connectivity. So what about this case? What is the difference we are getting? For that, let us understand one few things. If we consider T with the following class of matrix weights, the Laplacian eigenvalues are non-negative, and rank is n-1 of S. So the first S eigenvalues are 0. So that's why the lambda S plus 1 is the first non-zero eigenvalue. And we denote it to mu T similar to the algebraic connectivity to make the keep the consistency. And we found the following. In this case, this kappa T, whatever the constant we define, is always less than or equal to mu T, the smallest eigenvalue as lambda S plus 1. And there is equality obviously attained for positive weights, as well as we can clear example where the positive, this equality may attend when the matrix has nothing. But there are examples that inequality also stays. So these are the basic three results we are able to prove. And the first paper is the results I presented from. It is in archive. The second, the other two papers are the results I quoted. Thank you.
Okay, thank you. So, any questions or comments? No? Okay, so we are anyway delayed, so this. No.
Myself, Sumit itself. Yeah. Hello.
Hello, yeah.
Yeah, myself, Sumit. I like to thank organizers for giving me this opportunity because I didn't mention that in the talk itself.
Yeah, anyway, we'll get another
really
chance.
thank you for this.
Okay, thank you. Yeah. So our next speaker is Tony Thomas from Kerala University of Digital Sciences. It's graph centrality measures and mobile malware detection. Yeah.
For the organizers for giving me an opportunity to deliver a contributory talk in this session dedicated to Professor Arvind Kumar Lal. I was the first independent PhD student of Professor Lal. The area of PhD research was a bit different from his area of research. I pursued a PhD in the area of cryptography during the period 2002 to 2006 under his guidance. The area of cryptography or the research in cryptography in India was in a developing stage only at that time. When I approached Professor Lal, he was very receptive and he, without any hesitation, he allowed me to do research in this area. And subsequently, I explored different related areas, and now I have doing research and academic activity in the applied area of cyber security and computer science. So in this talk, I'll be presenting a short work on graph centrality measures and their applications in mobile malware detection. This is a joint work with one of my students, former PhD student, who was here. So, as you know, almost everybody nowadays uses smartphones. And we use different kinds of mobile applications for doing many things. Are these applications really secure? Are they doing anything else which they are not supposed to do? Are they doing only the things which they are meant to do? So these questions relate to the security of the applications we use. I think almost all of you using one or other Android application for day-to-day activities. Okay, in this work, we will present the applications of graph centrality measures, detecting what are called malware applications, that is applications which can harm you. Right, so we use the concept of centrality. It is an important concept in graph analytics. Centrality is a very important concept in identifying the important nodes in a graph. There are different kinds of centralities like node centrality, eigencentrality, page rank, closeness centrality, betweenness centrality, path centrality, and so on. So these centrality values may be computed locally based on information about a node, or local information about a node, or global information. We will be using a few of these centrality measures for our application. So first we look at a degree centrality. Degree centrality method defines the importance of a node in a graph as being measured based on its degree. So if it's an undirected graph, we have degree. And if it's a directed graph, we have in degree and out degree. So the in degree, out degree, or the degree measures how much that node is connected to, or how much that vertex is connected to other vertices in the graph. So in our work, we will be using in degree centrality, which is defined as summation j is equal to 1 to n aji. Aji is the number of edges from the jth vertex to the ith vertex. The second kind of centrality measure is the closeness centrality. Okay. Suppose we want to send a piece of specific information to each node of the graph, and we want to select a node in the graph that can transmit it quickly to all the nodes in the graph. Right. So we want to identify which node or which vertex in the graph is closest to all other nodes in the graph. Right. So the closeness centrality calculates. Closeness centrality metric defines the importance of a node in a graph as being measured by how close it is to all other nodes in the graph. It is defined as the sum of the geodesic distance between that node to all other nodes in the network. Right. So if a vertex or a node is closer to all other nodes, it has high closeness centrality value. If the distance of one node from other nodes are very high, then the closeness centrality value is less. So it is calculated as n minus 1 divided by summation j is equal to 1 sigma j, where n is the number of vertices in the graph and sigma j is the length of the shortest path from the jth vertex to the ith vertex. The third centrality measure we use is the betweenness centrality. So betweenness centrality measures the importance of a node in a network based upon how many times it occurs in the shortest path between all pairs of nodes in a graph. So how important that node is in the shortest path, or whether that node is involved in this communication between different nodes. Usually communication in many practical problems, communication occurs between two nodes through the shortest path. So whether this node is always involved in that communication. So how important that node is. This is measured by the betweenness centrality. So it is defined as summation j is equal to 1, summation k is equal to 1, sigma j ik divided by sigma jk. So we can count the number of shortest paths between the jth node and the kth node passing through the ith node. How many such shortest paths are there? Then what is the total number of shortest paths between jth node and the kth node? We take the ratio. We sum it up for all possible nodes I and j. That is for all possible nodes j and k. So fix the ith node, consider shortest paths between jth node and the kth node, consider all shortest paths between jth node and the kth node, then count how many are passing through the ith node. So that number divided by the total number we take. Then we sum it up for all possible node pairs, jth node pair and jth node and the kth node. Right. So this betweenness centrality, nodes having betweenness centrality are the nodes that are on the shortest path between large number of pairs and nodes. Hence they are very important or crucial to the communication in a graph as they connect to a high number of nodes with each other. The fourth centrality measure we use eigenvector centrality. This metric measures the importance of a node in a graph as a function of importance of its neighbors. So far, the other metrics were measured based on importance of that node. But eigencentrality measure actually measures the importance of the neighbors of a node. Right. It measures the importance of a node in a graph as a function of importance of its neighbors. So a node becomes important if its neighbors are important people. Right. So if a node is connected to highly important nodes, it will have high eigenvector centrality. Right. So if your relations are powerful, you are also powerful. Right. So it is measured like this, summation, so 1 by lambda summation I is equal to 1 to n eij upon into aij. That is, there is a small typographical error. It is nij here. Nij is defined as equal to 1 if aij is not equal to 0. So nij is equal to 1 if there is an edge between, or eij in this equation, c to si is equal to 1 by lambda summation I is equal to 1 to n eij aij. Eij will be equal to 1 if aij is not equal to 0 and 0 otherwise. That means eij is equal to 1 if there is an edge between ith node and jth node. And aij is the number of edges between ith node and jth node. right? And lambda is the largest eigenvalue of the adjacency matrix. So we will be using these basically these three centralities, that is closeness centrality, betweenness centrality, and eigenvector centrality for solving the malware detection problem. So let me come to the applications. Applications in Android malware. So we are looking at the application of the centrality measures in Android malware detection. So nowadays we use smartphones. Most of the smartphones are Android based. You are iOS based and you are Windows based, but majority of the smartphones are Android based, and there are many other devices which use Android operating system. So, and we use plenty of apps. With different apps, you can transform your humble cell or your phone and do many things. You can make it as a movie theater, workstation. You can attend conferences. You can do online banking. You can do shopping. You can book your gas all through apps. But how secure are these apps? Unfortunately, finding secure Android apps is a challenging problem. Every day, new and new apps are coming, and many apps which are coming contains what are called, or they involve malware, or they have malicious intentions. So suppose a user downloads a game and the game installs. Right, the game may contain some codes which do some malicious activity. So the malware operates inside the phone and it can become a botnet. That means it can send, or it can itself act as a source which attacks other mobile phones. Right. So without unknowingly, you also become a cyber attacker. Right. So the malware gets, or the application which contains some malicious code gets installed in your phone when you execute the application, and this application can do a variety of things. It can send unnecessary SMS without you knowing. It can make unnecessary phone calls. It can make your webcam open without you realizing it, or it can become a bot. That is, it can act as a botnet. Botnet means the term we use just like a robot. It's a part. It acts its own and do malicious things, like sending again this malware codes or malware apps to other mobile phones, the network, and so on. Right. So malware or malicious software is a software designed to do unauthorized access to computing systems. So nowadays almost all people are using smartphones for various kinds of things, usually just for making phone calls. So we use a large number of third-party applications. Right. We don't know how secure or what really these third-party applications are doing. Even we have the Google Play Store, and there is no guarantee that the applications you find in the Google Play Store are all safe. There is no guarantee that the many applications released by even government agencies are fully secure. So an Android malware app, that is an app which does malicious activities, can perform different type of activities like stealing your private information, sending SMS to premium rate numbers, to surveillance. They can they can keep on tracking your locations, your activities. They can switch on your switch on your camera. They can send your GPS locations, record the phone calls, encrypt the data, and ask for ransom. They can lock the device. They can pop up advertisements, so on. Or if a malware gets infected or installed in your phone, the attacker may be able to fully control your phone also. There are many antivirus products available. There are many mechanisms available. Unfortunately, these malwares are evolving day by day, more and more complexity. So it's very difficult to detect and prevent emerging malware. So usually this is what happens in an Android application development. So we'll have a source code, assets, resources, manifest, all these are compiled, and an APK file is created. So an application basically appears as an APK file. Now the Android OS provides what are called APIs, or application programming interfaces for accessing vital resources like such as camera, GPS, microphone, telephone, etc. So this facility is actually exploited by the people who develop malware codes. Right? They will use this API calls in various combinations. So by using API calls in various combinations, they can switch on your camera, they can make your device to send unnecessary SMS or unnecessary phone calls, etc. So the API calls you can find in the code of the application, the source code of the application. That will work only if each of these API calls require certain permissions. Only if these permissions are given, then only these API calls will be able to work effectively. Right? So when you are installing an Android application in your phone, it may be asking you to grant several permissions. Right? You will just click and give the permissions. Right? Then once the permissions are there, when the application executes, it makes what are called as system calls. It interacts with the operating system, which is called the kernel, and it produces system calls. Right? The system call sequence contains relevant information about actual malicious behavior of the application. Right? So if it is using or switching on your mobile, your webcam, if it is switching on your camera, or if it is accessing your GPS, or if it is encrypting the files, all these will be reflected in the system calls generated while the application is running. So basically an Android application will have permissions in Java code. The Java code will contain the API calls. So the API calls require the permissions. Once the permissions are there, the system calls will be generated. So basically there will be a user mode and there will be a kernel mode. Right? When the application program executes, the program switches from user mode to the kernel mode. In the kernel, that is operating system level, it produces several system calls. So the system calls, if you analyze the system calls, you can identify whether the application is a good application or a bad application, whether it is a malware or it's a benign application. So that is overall the idea. Right. So there are many Android malware analysis or detection techniques. They are classified into three categories: static analysis, dynamic analysis, and hybrid analysis. Static analysis, as the name indicates, we do not execute the application. We take the application, decompile it, analyze the code, and see whether the code of the application contains suspicious things, whether there are some suspicious permissions or API calls, or how the control flow goes. Right. By analyzing those things without actually running the application, we may be able to infer whether the application is a malware or a genuine application, a benign or a goodware application. Right. The next type of analysis is the dynamic analysis. We run the application. When the application runs, it produces a lot of dynamic features, like it makes some of the API calls, system calls, then you can see the CPU usage, memory usage, and the flow of packets, etc. So all these dynamic features can be analyzed to see whether the behavior is a malicious behavior or a normal behavior. Hybrid analysis uses a combination of static and dynamic features. Static analysis have a lot of limitations, right? And many malware or malicious Android applications cannot be detected by analyzing the code by using the static analysis. Dynamic analysis, therefore, is different, but dynamic analysis has the danger that you have to execute the application. Usually, we execute the application in a protected environment. So this execution will take time and analysis is more complicated. So in this work, we will be doing dynamic analysis. So we run the application and the application will generate several system calls. These are a set of system calls which an application can make. System calls are received from IOC, send to, write to, close, bind, make that, change mode, etc., etc. So I'm not getting into the details of all the system calls. For convenience, we code the system calls using these letters A, B, K, C, E, F, G, etc., A, B, C, D, E, F, G, etc. Okay. So watching what is a Trojan. A Trojan is a special kind of malware. Right. It is a type of malware which looks like an innocent application, but within that, without we realizing it is doing many malicious things. So watching what Trojan is a corrupted version of a war context application. Use smartphone camera to display the world to the user while they send SMS messages. So when if this Walmart Trojan is installed, you can access your contacts, you can locate for the GPS, make phone calls, do a lot of things, right? This is one malware or one example of a malicious application, right? Just for illustration sake, I have taken this one, talking about there are thousands and thousands of malicious Android applications. So if I execute this Walmart Trojan, what I am getting is it will produce a sequence of system calls. You can see in this figure the system call is A, etc. These are all different system calls when this Walmart Trojan executes in it. Right. So this execution can be represented as a graph. That is the problem. That is, so you can see that this is a limited version. Right. So it's the nodes or vertices of the graph correspond to the different system calls. System call D is there, system call C is there, system call D is there. So if system call, you can see that there is a loop in the system call C. That means system call C will be followed by system call C again. Right. Then there is an edge from system call C to B. That means in the system call sequence, you can see system call C followed by system call B, etc. etc. So in this way, you can form a directed graph by selecting the system call sequence of the application. So you just run the application, select the system call sequence. The system call sequence can be modeled as a directed graph. Once you have this directed graph, you can compute the centrality measures like integer centrality, degree centrality, between centrality, cross centrality, eigen centrality, and so on. Okay, so from this, by executing this Walmart Trojan, we compute this shortest distance matrix like this, and this produces the system called A, B, C, D, E, F, G, H, etc. And when we execute for 1 second, the system called A occurs 116 times, system called B occurs 641 times, etc. etc. So, and this is the shortest distance matrix. From A to A, the shortest distance is 0. From A to B, we compute the shortest distance, which is the number of edges from A to B. For going from edge vertex I, A to vertex C is 1, then shortest distance from A to C is 1, and so on. So we calculate the different centrality measures. The integrity centralities are this, and then the eigen centralities are this, between the centralities are this, cross the centralities are this. Right. So given any application, we can execute the application and form a graph and calculate different centrality values. So these centrality values will give some idea about whether the application is malware or goodware. That is the idea. Right. You can see that in this case, for different vertices, the eigencentrality have different values. For example, system called A, the eigencentrality is 0.4, but for the between the centrality for E is 0. So what we do is, this is actually what is called a classification problem. Given a Android application, whether the application is a malware or a goodware, or malware or a benign application. So that is what's called a classification problem. Right. So this classification problem is solved using machine learning techniques. Right. So machine learning techniques, what they require is we need to train the machine learning model with the data. Our data is goodware and malware applications. We train different machine learning models with the goodware and malware applications. Once they are trained, training means we fix the parameters of the model using this a set of the data corresponding to malware and goodware. The data we take are, we calculate what are called features of goodware and malware applications. The features are, we execute different applications, goodware applications, malware applications, calculate the eigencentrality, between the centrality, and cross centrality. So these three-dimensional feature vectors associated with each application. Right. So each application, whether it is a malware or goodware, we associate this, we run the application, compute these three centrality values, and associate this three-dimensional feature vector with each of these applications. Right. So the malicious behavior and application is detected from the centrality method. We use actually ensemble learning method. Right. So what we do is, we ensemble learning, what we do in this case is we take a machine learning classifier, and we take the between the centrality as a feature vector. Right. Then we train that model using the between the centrality values of many malware and goodware applications. Right. Similarly, we train another machine learning application, the machine learning model, another machine learning model with the eigen centrality as the feature vector. Then a third one with the between the centrality. Okay. So we will have three machine learning models trained using these three centrality values of the features. Now, when a new application comes, that we need to classify whether it is a malware or goodware. What we do is we run the first machine learning classifier, and then that first machine learning classifier will say that this is a malware or goodware by analyzing the between the centrality value. Then the second one will classify it as goodware or malware based upon the second centrality value, say eigencentrality value. The third one using the closeness centrality value. Right. Then we club these three results and make a final prediction. If two or more are saying that it's a malware, we declare it as a malware, otherwise it's a goodware. So we constructed a data set consisting of 2,000 malware and goodware applications. And we use 80% of this data for training, that is getting the parameters of the model, and the remaining 20 we set. And we used the metrics like accuracy, the precision, etc. And we used these machine learning models, the decision tree, the support vector machine, artificial neural network, and random forest, and we obtained these results. And you can see that we got an accuracy of 0.97 when we are using a random forest classifier. And with these features, with a random forest as a machine learning classifier, we obtained a very good accuracy of 0.97 in this malware and goodware. And this is the value with the decision tree. We got an accuracy of 0.91, and the artificial neural network 0.88. The support vector machine we obtained 0.87. So these are the results when we use these three features together. That is the eigencentrality value, between the centrality value, and the closeness centrality value. But if you are just using one centrality value as a feature, you can see that accuracy is a little bit less. If you are using considering only the between the centrality value, you are getting an accuracy of 0.82. If you are using only eigenvector centrality as a feature, then you are getting an accuracy of 0.82. Closeness centrality, you get a better accuracy of 0.93. So in our model, we use these three features, that is the between the centrality, closeness centrality, and eigenvector centrality. So our model is like this. Given an application, we want to classify whether it is an malware or a goodware. We execute the application, collect the system call sequence, form the system called digraph. From that system called digraph, you calculate the between the centrality, eigenvector centrality, closeness centrality of all the vertices. Right. This is the feature vector, and we use that feature vector by analyzing, putting this feature vector into these machine learning classifiers. We can determine whether the application is a malware or a malicious application or a benign application. Okay, so these are the references. References are a few of the references that are basically our own publications. Thank you all.
Thank you. So, any questions or comments? Well, it is very nice to see applications of mathematics we do in real life. Very nice. So thank you. So I also would like to thank all the speakers of this session. So with this, I think the technical session comes to an end. Thank you.
Thank you, professors. I also thank Professor Rajaram Bhatt for chairing this session. Thank you very much. Before moving to next session, there is a small announcement. I kindly request all the organizers and speakers of this session to keep your camera on after the end of this session so that we can have a small photo session later on.
Okay, sure, thanks.
I now request Professor Sukantapati to organize the next session. That is a session of tribute from Professor Lal's friends and colleagues. Professor, please.
Okay, we have many interested who want to pay tributes to Professor Lal. Can we? Some people have submitted videos, I think. Can you play some of them? Yeah, Vikas Bhattacharya. I request Vikas. Yeah, continue, please.
Hi everyone. At the outset, I wholeheartedly thank the organizers of this conference for arranging this session to pay tribute to my PhD supervisor, our respected and beloved sir, late Professor Arvind Kumar Lal. Hi everyone. Hi everyone. At the outset, I wholeheartedly thank the organizers of this conference. Hi everyone. At the outset, I wholeheartedly thank the organizers of this conference for arranging this session to pay tribute to my PhD supervisor, our respected and beloved sir, late Professor Arvind Kumar Lal. I really do not know exactly what I should speak in this speech to pay tribute to him. I cannot find appropriate words to express my deep sadness. My deepest sympathy goes out to his family members who had to deal with such a sudden loss. Several months had passed since the death of untimely and sudden demise of Sir. But still, I get it hard to believe that shocking news. This is perhaps His loving presence is within us, and I am sure He will always remain with us. His teaching and research guidance was always accompanied by His loving and caring nature. Anyone who got acquainted with him surely aware about his kindness, generosity, broad-mindedness, loving and caring nature. Sir was not appointed as my PhD supervisor initially. Due to some personal reasons, I had troublesome days just after the coursework was over. I almost planned to quit the PhD program. With the suggestion of a friend, I knocked the door of his office one day, with a lot of hesitation and fear. That day, I can never forget. His encouragement, loving, caring, and inspiring words, and above all, his personality quickly changed my attitude towards life and career. He encouraged me to carry on and accepted me as his PhD student. Whenever I approached him or knocked his door to discuss something, he was always ready and available. I do not remember a single instance that he turned down. During my PhD studentship, he was appointed as gate chairman. He even called me to his gate office at several occasions to discuss about my research, even when he was too busy and under pressure with lots of administrative work. I am really inspired by his coolness. It is very hard to find such an academician, researcher, good teacher, and a great human being. With his guidance and blessings, with his kindness and generosity, I could finish my PhD smoothly. I feel so privileged to have him as my PhD supervisor. I thank God for having been given the opportunity to be supervised by such a humble genius. You rescued me, sir. I owe you a lot, which I can never repay. Thank you ever so much for everything, sir. Sir, you are the one for whom who I am today. I always aspire to be like you. There are dozens of other instances I know when he helped others at their difficult times. All those concerned persons must be remembering him with a lots of gratitude. After my PhD was over, I got to meet him at several occasions. The last one in a small dinner in our residence, along with his family members. At this moment, every second of that evening is rolling like a movie reel in front of my eyes. At every meeting I had with him, I got his invaluable words of wisdom and encouragement. Those are the driving force of my life. I pray the Almighty to give us, His children included, the strength and inspiration to move His legacy forward. I know we all will remember him even though he is no longer with us. Let us make sure he is never forgotten. Thank you very much.
Professor Krishnan from IIT Bombay.
All right. Wanted to talk about a few memories. All right. Wanted to talk about a few memories I have of Professor Arvind Lal. So this is again with fond memories of Lal and my collaboration that I had with him. So let me start by saying that I've known Arvind only for a small amount of time as compared to the other speakers who would have known him for several decades. I somehow got to know him very well only in the last 1 or 2 years. And regretfully, I have only written one paper jointly with Arvind, and that is jointly with Arvind and Mukesh, and that has only been sent for publication now. It is not yet seen the light of the day. So, and this paper is somewhat it's non-standard. So, the via medium for that is my student Mukesh Nagar. He was my PhD student, and during his PhD, we had observed some inequalities about Laplacians, the two-road index by two-road partitions, and we had observed some data, and we had some hint of a proof, but there were some points which had to be filled. It was not a complete proof. There was definitely some gaps, and we had just written down as a small note, just so that we can start working on it whenever we want. Because later I found out that writing such things always helps. That is, you write down the background, and then you write down your data, and then you write down here is your conjecture or whatever. The result that you think is true. So I have several such notes, and one of these notes was done along with Mukesh, and he got a postdoc offer from IIT Kanpur, and he was a postdoctoral fellow with Arvind. So I think they had discussed it at some point. Then I had forgotten about it because it was about 3 years after Mukesh left, and I had another student. I was busy with other things, and suddenly I got a mail from Arvind saying that he has a solution. So I said, tell me. And then he sent me a sketch. It was very correct, and some minor things we had to do. And I told him, why don't you write it? It's very good. I'm happy to see it being solved. And Arvind very graciously said, no. These are actually the gaps that I've plugged in the write-up that you and Mukesh had. So let's, the three of us should write it together. So that's how we started work on this. And then we slowly started work to read more, more questions were raised, more questions. The project took on a life of its own, and eventually, we sent it for publication and all that. But anyway, that's how I got to know Arvind. Yeah. So my association with Arvind on the research front, when I got to know him very well, is only, this is 21, no? So maybe 2019, around the end of the year. That's when we started. And then 20 and maybe 21. So that's when we started working on, and then slowly stitched up few things, and more material were added, more pages, more material, so on. And then finally it took up, a shape of its own. And during this phase, definitely, Arvind is instrumental in getting this problem solved. There's no doubt about this. And it is about this work that I have spoken on this conference in honor of Arvind. So in fact, I'm grateful to the organizers and Professor Manjunath Prasad and others who have given me this chance to talk about my interaction with Arvind. So this solution, so we had almost done it except for one. If you look at the thing, there will be a last row. So there will be one last row in which something had to be done, and that in that last row we had to do something, and that involves a lot of study of path combinatorics. Yeah, and once we figure out that there were these paths coming, we had to read some basics about it, and I am not an expert in the combinatorics of paths, and Arvind told me neither was he. And so when I read something and I told him, Arvind was so thrilled about these results. He told me that he wanted to read this combinatorics of paths in way more detail, and he said, no, let's do it. From the word go, it was clear that I was a part of his plan. That was the way he is. And he sent me some papers, said he wanted to read this, and he told me that we should do something in the summer 2021, because he had some undergrad course that he was teaching, which has a large number of students, and then during that semester, actually, if you're teaching this large UG course, it's a little tough to do work. And in general, we had postponed it, but somehow, we never got to that stage. I regret that I didn't force him to do something together at that time. Yeah. So I remember, I mentioned this book, A Course in Enumeration by Eigner, and quickly he had a issue in the library. He started going through it. He was always a man of action. That was a good thing to emulate. Definitely. He was a man of action, and it was quite interesting to see him, do things quickly. And because of this, he was very busy he was teaching an undergrad course, I think calculus. He told me that the course name, it was not the calculus, linear algebra, one of those things. I don't remember exactly, so I don't want to pin down the course name with my faulty memory. But and once I had met Professor Neeraj Mishra from IIT Kanpur, who told me, Arvind is very conscientious as a teacher. He's a very serious man. So during the semester, he's very involved in his teaching, and so we shouldn't disturb. And which is true. I've seen him work really hard. So that is some point that I really admire in him. And he was also a referee for my next PhD student's thesis. Yeah, and the referee report came in 2 months. He was very good. He wrote it quickly, and then the other referee also sent the report very quickly. So it is very good to see, that the people have raised the bar for sending in reports for PhD thesis. So, and in this report, he raised several questions, on the contents of the thesis. And as far as I know, they're all open. I mean, so he is very curious, actually. This episode illustrates his curiosity and his ability to read in a lot in short time, despite his teaching commitment. So this happened around this January 2021. And that time he was teaching, this entry of the undergrad batch, which usually happen around June, July, and July end teaching will start. But due to this pandemic, the semester has been translated by 2 months, maybe 2.5 months. So instead of July end, October, it started October or November, something like that. So he was teaching actually, November, December, January, February, he was teaching. And despite his teaching commitments, he sent his report for his PhD thesis. And it was a very good report. I'm quite happy with this. Just to see, what he has written and all that. His curiosity, that is the fundamental point that is to be observed, and it is worthy of emulation. Yeah, and if you look at our emails, no, that when in the collaborations that I had, suddenly there would be a burst of emails. Suddenly he would send me something, and then I would send back some email, and then he would send back, I would send, it just like a volleyball of emails just went. You can see about 12 emails I think went around 30 hours. And we had our own schedule, but suddenly an email will come, and then when I try to open it, I don't understand because it's not. He's writing it in terse language, and then I ask him, are you saying this or this? And then he will write back saying, no, I'm saying this. And so the email exchange is very, very intense. That is so. Within that short time, it was clear to me that he had a solution, and it was clear to him that I was looking for something more than what was actually there. And we exchanged a lot of ideas, and eventually, we have some result about which I have spoken in this conference, and it is very, very, very nice work that we collaborated. It was very, very nice to work jointly with him. And this probabilistic interpretation, there is one thing that was done after. At that time I was not discussing with him. Somehow I just didn't do it. I in fact did it after his demise. And I would like to know his comments on the result. It's because he always had some, yeah, this result is good, but maybe we can do something else. He had some comments which we don't publish, but it's always good to have these comments about what people think is good, what people think is not good. That reflects their taste. And it's good to know, that this person likes this and this person doesn't like this. So that kind of opinions you can, the information you can get, and then based on that information you can form opinions. So he's strong on combinatorial, he's strong on graph theory, he's strong on algebra, he's strong on topology, things like that. For that I would like to collect data. I would like to see more his comments. But yeah, that's that. So overall, as I mentioned before, I got to know Arvind for only a reasonably short period of time as compared to other people here. And however, I have met him before several times. There was an ATM in Banasthali, I think 2017 or 18, I don't remember now. But that time, there was maybe 17 or 18, in which he had spoken, Professor Sani had spoken, and I met him. I had met him in Banasthali, and we were generally chatting around. We walked around one night and all that. So that time around, we were just we were jointly lecturing and we were chatting. It was good, but we never had any project going on. And how I wish I had started work with him earlier, because he has raised several questions which we will try to do something. And it's I will definitely remember our collaboration with a lot of fondness, and I cherish the memories we had. And sometimes you feel it's just not right. It's just not right that he left us so soon. It's just not right. But what can we do? There's not much choice that we have. So the only thing that I can do is I remember the activities we did jointly with fondness, and I will tell people, there was this Arvind Lal. Later I will tell everybody I met. There was this person Arvind Lal. He solved a problem that both me and my student couldn't do, and we wrote up a joint paper. And then I met him. I'm fascinated by his curiosity, by his ability to put in hard work, and how I regret not having started to work with him earlier. So overall, I think I would stop here and say that I cherish my time with Arvind Lal, and thank the organizers again for their for giving me this opportunity to talk about our joint work and the time I spent with him, with Arvind. All right, thank you very much.
Professor Anish Sarkar.
Good evening, everyone. It's a sort of, I don't know, it's a very sad that I have to speak about Arvind Lal's memory, which there are so many. I did not have, I did not really work with him academically, but he was a very good friend. We spent 3 years in the hostel, and in ISI hostel he was my so-called bathroom mate, because in ISI hostel we had 2 rooms which used to share a bathroom, and he was in the other room, and we shared the bathroom in that sense. And I have known him since 1989. So we shared these bathrooms, so-called, from 91 onwards, and we used to have a lot of interesting conversations, and many of sort of my memories goes back to the fact that I think he was the most jovial person, large-hearted person that I have ever met. There are always friends of him who'd come to the hostel. I remember somebody called Mr. Jhaji, who used to come and used to spend 3-4 days. And there's a friend of him called, I think his name was Ajit. He used to come, and they will stay a couple of days. And even when there are some times when Arvind was not there, and so once Mr. Jhaji came, and knowing Arvind, I of course opened the room for him, and Arvind came in next day after, and of course he was very happy that that I did this for him and so on. And we used to spend a lot of in the night. He will come through to my room and we'll chat for several. Sometimes even hours on general stuff, and he was very open from every point of view. So my regret is that I have never worked with him academically, except that at one point of time I had asked a question on matrix algebra on some eigenvalue problem. I had some kind of positive matrix, some expectations. So since I work in probability, everything is to do with probabilistic questions. So I had some sort of vectors whose expectations on different time points, etc., formed a matrix, and I wanted some information about the gap between the largest and the second largest eigenvalue, etc. And Arvind actually came back with a solution couple of days later, though unfortunately we could not use this because our sort of intuition on the thing that this gap would be a significant in our study of that problem, probabilistic thing, was flawed. And so, but his result was of course correct, that if there were some estimates on this gaps or the spectral gaps or whatever that he had given us an estimate. So that is the only time actually I have talked to him about academics. But otherwise we have spent a lot of time. My last talk with him, which happened sometime probably in January or February, I don't remember, and it is also very accidentally, in the sense that my wife has an uncle whose name is Arvind, and I was trying to call him, and by mistake I called Arvind Lal. Instead of Arvind Kumar, I called him Arvind Lal. And so I asked him, so actually I should say in Hindi, so uncle, how are you? Chacha ji, kaise hain aap? And then he said, अब तू भी मुझे चाचा बोलने लगा है. So that was the thing. So then I, of course, and then he laughed, and I realized that I have called Arvind, and that's how his laugh was so infectious. So it's a very unfortunate thing that I mean, I am still cannot believe that Arvind is no more with us. I do not know how to express anymore anything. It's just too sad. I do not know. I think I will stop here. Thanks everyone for listening. I hope his family, Niyoti, and his son and daughter would recover, had recovered. And I cherish the memories of Arvind all the way. I'll stop here. Thank you.
Professor Rajaram Bhatt. Rajada.
So, hello. Yeah. Okay. So to begin with, I wish to thank Manjunath and Sukanto, the organizers, for giving me this opportunity to go back in the memory lane. Arvind, actually called Lal because all of called him as Lal, is my classmate. So, as you know, he moved to ISI from Delhi University to do MStat, whereas many of us, actually whole batch, moved from Calcutta to do MStat second year. So we are in first year in Calcutta and then moved there. It was a big, noisy batch of mostly Bengalis. So the language of the hostel became Bengali, and so he was sort of forced to learn some Bengali. And he was everybody's friend, sabka dost. So he was very fond of football, cricket. He used to play also badminton, table tennis, everything. But I think he was the top player of carom. So most of the days you would see him, day or night, you would see him in the common room playing carom. And he would be upset if you put the newspaper on the carom table because he would maintain it so nicely. And so, like often there are people looking for Arvind Lal for some help or the other, and we always send him to the common room, and you would see loud laughter every now and then from him. So then there are many things to remember, and so I would like to recall like the Sabji Mandi visits. Like things were different in those days. Now you order vegetables, they come to your home, but then we students used to maintain the mess. So for that, every week we go to Sabji Mandi and bring the vegetables, large quantities, and it is a very messy, very crowded market, and getting things from there, bargaining them, and things are not easy. And always we needed help from Lal because if he's around, most of the problems are solved. And other things like even the handling mess workers, that was, we always took help from him because it was a very difficult job, because somehow there the institute gives us the money, the students, and the mess workers are actually workers of students. Workers pay them, and it was that kind of system. And managing them was not easy because some of them were very drunkard, some were short-tempered, some were just plain simple lazy. But to maintain them and get extracting work out of them was not easy. But Lal could do that. And similarly, educational trips. We had something called educational trips or academic trips funded by ISI. We could go to different places, and most often Lal used to manage everything, starting with booking and especially arranging food on the trips and everything. So he was very fond of food, good food, especially sweets, and he would everything to the last dot. So I also like make some personal note, like after our PhD got over, I went abroad to Canada, and my wife had to get the visa, Canadian visa, and she had to travel to Delhi and get the visa, and Lal was there, and Lal arranged everything, the accommodation and all the help for the transport, this, that. She even now remembers that. So many such things. Okay, so where she said he used to help everyone, and very jovial, very happy going person. And then after PhD, after a few postdocs here and there, he went to, as you know, he went to IIT Kanpur and settled there, and got married to his longtime pen friend. I guess the concept of pen friend is gone now with all this WhatsApp and Facebook, but or emails. But he married his longtime pen friend Niyati from Orissa. So he was from Bihar, married Niyati from Orissa. I'm sure it was not an easy job, but he did, and they two lovely kids. So I visited them many times. They also have come to Bangalore. In fact, some more visits were planned. He wanted to go and see Coorg, but twice when he planned, it was just raining heavily. I said, if you come now, you'll just see the rain, because you can't see the Coorg. It was August. It was just raining too heavily, so he could not come. So more visits were planned, but somehow it didn't take place. So I don't know, you can see from the students, he has helped so many people. And actually, when I think of Lal, I just think of this character, like those who know Kannada would say, like the Sudeep from number 73 Shantinivas, or those who watch Hindi movies, I would think of Rajesh Khanna of Bawarchi. So he would just bring happiness everywhere, help everyone. So that was his style. So don't know, Rajesh Khanna of Bawarchi. Yeah. So that was the way. Means it was so happy, and so I don't know, we would really miss him. So it was because his life came just an abrupt end. I'm sure his family would be finding it very difficult to cope. So we think we would always remember him as someone who spread just happiness and love wherever he went. So that was his life. So I think that's what I wanted to say. Thank you.
Professor Bapat.
Anybody else want to speak?
Do we have time for that?
If someone is there, then let us not disappoint them.
Yeah, true.
Whether Arup is there?
I don't know.
Okay. If nobody else is there, then let us proceed. Yeah, okay. Professor Bapat, please.
Yeah. I'll start when Arvind joined ISI as a student. So as it was mentioned, he came from the Delhi University background, which was a bit of unusual in ISI, because most of the students were either from Calcutta or from some other institute, academic institutes, research institute, and so on. Especially the master students were mostly from Calcutta. Very few from Delhi used to be there. Even now that is the case. And Arvind came from the Hindu college and with a Delhi University background. And also at that time we used to have a SQC and OR specialization. And Arvind had chosen that specialization. So that was also a bit unusual, that students normally took the advanced probability or mathematical statistics specialization. So they are better prepared for research. But Arvind took this SQC and OR, and that meant a lot of preparation, theoretical preparation for research. But he managed to do it without any problem. And so he started his PhD, and I'll just say a little bit, he was interested from the beginning in combinatorial ideas. He was not a statistics person at all. He had no statistics background as such, but he was purely a mathematician. And we started on the problem. I just gave him like something like a curiosity. We started working on, I'll just say briefly about it, that you take the characteristic, you take the adjacency matrix of, for example, of the path graph, and you take the characteristic polynomial of the path and evaluate it at some matrix. So evaluate it. So if you evaluate at the adjacency matrix of the path itself, then of course you get 0 because by the Cayley-Hamilton theorem. But then we started just playing with it and evaluate the polynomial at some other matrix, adjacency matrix of some other graph. So you take the adjacency matrix of the path graph, take the characteristic polynomial and plug in adjacency matrix of some other graph. So we did some experiments and Arvind very soon noticed that they all turned out to be non-negative matrices. So that was a bit of a curiosity that why they are coming out to be non-negative. And with pure brute force, he was able to establish many such properties about the non-negativity of the matrix. And we thought it was interesting and we started developing it further and got several results which eventually led to his PhD. And in the meanwhile, we got to know connections with other problems, deeper problems. In fact, his thesis went to a very great mathematician of that time, Professor J.J. Seidel, and Seidel enthusiastically supported his thesis and wrote a very positive report and led us to some other important work in the area, especially work of some French mathematicians, Delaharpe, and it was realized finally that we had another very simple combinatorial way of looking at characterization of Coxeter matrices or what are called Lincoln diagrams. So eventually it started fitting into a very broad, well-known developed theory with a new viewpoint. So that was the story of his PhD thesis, and his combinatorial skill was quite evident even at that time. And after PhD, I don't remember helping him at all for a position or anything. He himself went to TIFR, and Dayanand Verma liked him very much. And that is where I think it helped him a lot. He got the TIFR background for a year and so got to learn quite a bit. And also the contact of Hiralal Janwa, I don't know how he found, but later on he got into contact with Janwa and went to Puerto Rico. I think he was there almost 2 years, I think. That's where his daughter was born, perhaps. And then he joined IIT Kanpur. So I think I don't remember doing anything much for his placement or putting him into a postdoc. That was not required in a sense. And wherever he went, he made himself quite indispensable because of his nature of just throwing himself into anything where it was required without bothering about other activities or leaving aside what he was doing at that time. And this continued later. I mean, of course, people have talked about his helping nature and so on. So when Raghavan wanted to visit Allahabad for some, first of all, he wanted to visit IIT for academic lectures, but also nearby places. So he wrote to Arvind. I mean, he got his contact. And Arvind did not stop at just arranging the guest house and arranging a talk. I mean, that is the minimum thing that we do. But he went way beyond that. I mean, he made sure that the visit was absolutely perfect in each and every respect. And not only that, he made instructions for the guest house for vegetarian food, and he arranged small parties in his house where some Tamil faculty was present, like Nandini was there at one time, or some other people. This was not at all required, but he made it sure that the visit was very comfortable in every respect, and throughout his visit, so his trip to Allahabad, and I think he visited once or more than once. And I think actually when I wrote to Raghavan about the news in this March about passing away, then Raghavan wrote a very, very passionate and long letter about his experience with Arvind Lal and also his experience with Niyati and how they arranged for his visit and made sure. So these are the experiences that you get to hear from other people about how he, dealt with everybody that came in contact with him. And we have talked about student trips, so I also remember a couple of trips that I was accompanying them, I think once in Madhya Pradesh and also Rajasthan. So when Arvind is sure, when Arvind is there, we are sure that he will again make everything as perfect as possible. I mean, he will go to Delhi market and bring a big bag of apples just for us to consume during our trip. So he will not leave anything, no stone was left unturned to make all the things perfect. And this is always with his usual typical smile and Bihari accent, which was a very sweet accent that he had. And so this was always, I mean, you knew that you had something, somebody whom you could depend on about anything. And combinatorial strength is something I realized always. Actually, it was my habit. Whenever I wrote something, if it was not a joint paper with him, individual paper or with somebody else, I made it a point to send it to him first before sending it anywhere, and just to ask him to read it and make comments and give his suggestions. And most often than not, he would make some very critical. He found critical errors. I mean, he made sure to not just correct the typos and so on, but he found actual mistakes. And later on, I stopped that practice because I realized that it was taking time from his busy schedule. So a few years later, I did not send him my papers like that, but I have several of my papers have gone through him before doing anything further. So I think many of us have said very fondly of him. I also want to add that, especially his family they should get the strength, and all of us, his students, colleagues, former colleagues and friends, and colleagues at IIT and other places. I think we have to survive this kind of thing that has been thrust upon us, and hope that we get the strength and we can carry on with his memory. I think this was a good occasion that we got a sense of community. I mean, all of us got together, and many of us were influenced by his presence and actions. I think at least this will give us some relief, and we can continue to carry on in his absence, somehow get used to it, and hopefully do that in the future. Okay, so I think I'll stop with that.
Shall we proceed with the vote of thanks?
Yeah, sure.
Okay. I just have one or two lines to say. I thank all the speakers and all the participants, all the people who attended. I really thank them to make it a successful event. And also I thank Professor Manjunath Prasad for making this session possible, because earlier the conference was and it was already planned, but he made this possible. Yeah, so yeah, thank you. I will stop.
Yeah, probably we all can gather in the lobby with the camera on. Raksha, please coordinate.
Yes, sir. I kindly request all the delegates to please switch on your camera so that we can have.
T square. That's 2t square. 1 plus t square.
Kamal, please put on your camera.
Professor Kamal Lochan Patra, can you please switch on your video? I can also see Professor Simo Puntanan. Sir, if you can please switch on your camera.
So my camera is on.
Kamal's camera is not on.
No,
But
Kamal
I can,
camera is on. I can see.
I can see also.
Rajaram is not here in. You did not bring him in. Raksha, is that all?
Professor Sharat Sane, can you please switch on your video? Sir?
No, he is on. Maybe light is not enough. What about Thomas Matthew?
Is that better now?
Yeah, right. Lal's other students, only one is here.
I request the organizing committee to please come on the dais.
You are inviting organizing committee members, right, to be there?
Yes, sir. Yes.
Maybe towards the end we can. Anyway, you already made announcement. Okay, we'll come in.
So we may leave, or is it still going on?
I have no idea. I am also with that announcement.
Yeah, I think there will be one photo there, group photo.
how is that group photo going to work? I'm not sure.
They have already taken or not?
I mean, I think they can only do screen capture or something like that. I'm not sure.
Yeah.
All, I think with all camera on, maybe they will take a screenshot kind of thing.
Yeah,
screen capture. Yeah. But main thing is that has that been taken or not taken?
Oh, yeah. I'm not sure.
Thanks a lot, Professor.
Okay, I think then we can leave.
Thanks a lot, professors.
Okay, thank you.
Okay.
Thank you.
Thank you. Thank you.
Thank you all of you for organizing this. Thank you very much.
Raksha, please explore if Steve is there around. Steve Kirkland.
Okay, sir.
So you can see because what you
Simo is there. I saw him.
No, sir, he is not here.
Okay. It is all right. Then we'll proceed with the valedictory. Maybe before Bapat and Simo making their remarks, other participants can come forward and give feedback and remarks, if any. From participants first, participants and guests.
I request participants to share feedback. If there are any suggestions, opinions, or remarks, kindly raise your hands so that we can unmute.
I'm not seeing any raising hands. Do you see, Raksha?
No, sir, no.
Then you request Simo to come forward and give his remark. There is somebody raising hand.
Yes,
please.
yes.
Yeah, hello everybody. My name is
Please
Abdullah
put on
Azmi.
your video and talk.
Yeah, my name is Abdullah Azmi from Kuwait University. I would like just to thank everybody in the organization committee for such a wonderful conference virtually. And I really hope that some year in the future we meet in person. That's it, my friends, and thank you so much for all your work and efforts.
Thanks for your words.
Thank you.
Thank you. Any other participants wants to share the opinion?
Yeah, we have organized this particular conference with the all amateur team. None of us is a professional in managing this new technology. Somehow we have managed. Of course, there were many errors that adds some extra knowledge for us. And anyway, Simo, please. Raksha, bring Simo in. What happened?
Sir, sir, he is not in the teams now.
No, he was here.
Yes, he was there. Now.
He may join in. Just check. He might have quit for some technical reason. Anyway, we can request chairman of SAC to come forward and give his closing remark.
Okay, I think so. We have come to the end of a very busy and packed 5-day conference. I will say mainly about the second half, but even the first half, I could attend as many talks as I could. It was a very full program and a huge variety of talks. So I think people have shown great enthusiasm in participating and sending papers. And even the last 3 days of the ICLAA, I think the quality of the overall program has been as good as the previous conferences. I don't see any difference just because it's a virtual conference. The variety of problems presented and the new people coming forward was really very interesting to see. And the talks were also high quality. And actually, it was a hybrid conference. So those of us who could not be present sort of felt that we are missing something, because occasionally we could see people gathered in the auditorium and they were having an actual live experience. But for us, it was a remote kind of virtual experience. But still, overall, the subject matter dealt with was quite up to date, and I'm sure that it will result in good proceedings of the conference. So I again want to sort of wish all of you all the best in your further endeavor and further completion of the projects that you might have started with this conference. And let us look forward to such events, more such events in future. And again, my thanks to the local organizing team. I can only realize how difficult it is to manage all fronts, the video virtual front and telephone conversations and joining, especially the time constraint in the sense of different time zones. That is what makes it really, really challenging. But I think it was all done with great sort of professionalism, and overall it was a very wonderful experience. Okay, thank you very much.
Thank you, Professor. I think Professor Simo has not joined yet, sir. Sir, please unmute.
Yeah, I must be audible now, isn't it?
Yes,
Am
sir.
I audible?
Yes.
Okay, we are coming towards the end of this ICLAA 2021. So it is my duty to thank everyone. So being the convener of Scientific Advisory Committee, it is my duty to thank everyone who contributed to the success of this conference. This conference should have been held in December 2020, but for the reason you all know, we have rescheduled it to December 2021, hoping that situation would be normal. Unfortunately, the situation remained uncertain, though we found some improvements. So we have continued with the decision of organizing this meeting in a hybrid format. Though the meeting in this format is not comparable with the normal format of, we have got the opportunity to see one another on the screen and share our thoughts and developments of the subject. So on this occasion, I thank SERB SERB for awarding a grant to support ICLAA. I thank the Chief Editor of AKC International Journal of Graphs and Combinatorics for their consent on publishing a special issue dedicated to ICLAA. I thank Scientific Advisory Committee consisting of Professor Ravindra B. Bapat, Steve Kirkland, and Simo Puntanan for their appropriate time-to-time advice. Altogether, we had one mini symposium, which is common between IWMS and ICLAA, and 20 invited talks, 26 contributory talks. This consists of 29 invited speakers, 26 contributory, total 55 speakers from 10 different nations. Number of participants registered for ICLAA crosses 200 from 24 different countries across the globe. I thank all the speakers for joining us and delivering their work. Speakers list consists of many from across the globe, and it consists of Steve Kirkland delivering Hans Schneider lecture, Abraham Bourbon from Israel, Andre Leroy from France, TSS Rao, SK Jain, Adi Ben Israel, and Apurva Kare joined from USA. Sean Follett, George P. Stan joined from Canada, and Simo Puntanan from Finland. Other invited speakers from India are Professor Sharas Sane, S. Armugam, N. Ekamaram, S. Shivakumar, R. Balaji, Shivaramakrishnan Subramaniam, Murali Srinivasan, Anish Sarkar, Nandini Neelakantan, Tirthankar Bhattacharya, and many more. I thank Mahe administration for supporting us. I thank Registrar Mahe, who is also the chairman of local organizing committee, for leading us from the front. I thank Director of MIT and administration for providing meeting place and all required facilities. Also, I thank Department of Data Science, PSPH Mahe, Department of Mathematics, MIT Mahe, Department of Mathematics, SMIT Mahe, for their association with KRMs, particularly the respective HODs, Dr. Asha Kamath, Dr. Sudhakara, and Dr. Anjan Rai Chaudhary. I thank the faculty of these departments and other speakers for chairing different sessions. I thank all the participants making this meeting successful. I thank Professors Ramesh, Srimati Maya, Vasudeva Guddattu, Vinay Madhusudan, Viswajit Dev for being a part of local organizing committee. I thank research scholars Savita, Raksha, and Uma Shankara for working hard continuously from the beginning of start preparing for the meeting. I thank David Michael for his support in handling the web page. I thank Aniruddha, Pooja BS, and other research scholars from MIT for their supports. I thank Department of Data Science office staffs, Ms. Sudhamani, Ms. Shubha, and Mr. Vasant for their assistance. I thank Transportation Department, FIV, for their support. So I'm not sure whether I have covered everyone who helped me in this process of thanking. In case you observe, so please excuse me and thank one and all again. Shubha, you can, not Shubha, sorry. Raksha, please.
Sir, Professor Simo has joined us.
Is it? Yes. Simo, you would like to give some closing remark? I already given vote of thanks.
Hello, can you hear me?
Welcome. Yeah,
yes.
I can hear.
Actually, I think I on Wednesday evening, I more or less said what I had in mind. So I thank you very much deeply. You have done remarkable work.
Okay. So is it time to say goodbye to each other?
Yes.
Professor Bapat?
Yeah, I think we'll conclude on that note. I think it was.
Okay. Raksha, then let us conclude.
Thanks a lot, professors. Thank you, all the delegates, and thank you, participants, for joining us for 5 days. Thanks a lot.